this a little bit later. So in the DBFL, we are looking at, as I mentioned, manifold of processes from 3D printing of steel to Shotcrete 3D printing technology that we have invented in Braunschweig, to subtractive processes where we, for example, look into dry joints and connections for disassembly, but also collaborative robotic processes with alternative materials, as for example earthen materials, as in this rammed earth, robotic rammed earth project. Generally, we could try to cluster our topics a little bit, and we have lately come to a categorization where we say we have a couple of processes that work on material reduction, using less material, using more intelligent forms. We have a stream that where we have projects together also with Oliver Tessmann and that are addressing reuse, and recycling projects where we look into construction debris, how we can further use this or use materials that are basically infinitely recyclable. So let me start with the reduce stream, so to say. So as I mentioned, Shotcrete printing is one of the processes that we are investigating at TU Braunschweig. It's an old process, also invented 100 years ago, therefore well established in the norms and codes, and ready for implementation, also in the automated version in robotic Shotcrete 3D printing. The idea is that material is not simply deposited as streams, but it's rather jetted, and it has a pretty high throughput of material. We can print against vertical surfaces in a horizontal manner, for example, to include consoles or supports. We have a very good layer bonding between the layers because of the pneumatic pressure that the material is jetted onto the previous layers. Therefore, we can do gradual transitions from vertical to horizontal, which helps in the transmission of forces. And then we have sensors integrated into the process so that we have a higher control on this process. And what you can see in this video is, I don't know if it's visible, there's this red line. This is basically a laser that measures the distance between the nozzle and the printed layer. And if this distance changes due to some unforeseen factors, then the robot speed will be adapted so that after a couple of layers, this is leveled out again. So these are adaptive processes. As an Institute of Structural Design, we're also mainly interested in structural components. We're looking into wall-type elements, columns, spatial structures, and also hybrid fabricated structures as these add-on printed slabs, for example, where the floor slab is cast in a conventional manner, and then ribs are printed on top of it where the forces are dominant. So, of course, reinforcement is one of the major issues still in 3D printing, and we've developed a couple of different techniques to address this. The simplest one is that we are printing the geometry basically in a slightly undulated manner, then place horizontal reinforcement on top in between these layers, and then basically thread vertical reinforcement through those valleys that are created, and then apply a second layer of concrete that structurally embeds the reinforcement and hence produces fully structurally reinforced concrete elements. But since the forces in the structure are not predominantly orthogonal, we've also investigated how we could optimize the reinforcement placement and also automate it, and therefore we work together with the Institute of Adaptronics and Mechatronics at TU Braunschweig and developed this so-called dynamic fiber winding machine. And here's a short video of this process. So this is the material jetting process, where we print layer upon layer. Then we have a structural analysis of the forces, which is then automatically translated into a print path. And here, a strand that is winded with a helix around it is placed onto the wall with a kind of a stapling process, where a modified stapling gun is used to pin this material on top of the surface. And then the second layer is applied. And later on, conventional tools for surface finishing are used to soften and smoothen the surface. Meanwhile, we are in a little bit of better control of the amount of material that is applied, also through digital quality control. But basically, this is the fully automated process to create a load-bearing concrete structure. So, based on these ideas, or this is maybe something that I say in between. So digital quality control, I just mentioned it, to deal with excess material or material that is at places where there's too little or where some accidents have happened. We developed this streamline. Here you can see kind of the worst failure modes that can happen. We have sometimes the material was clogging and therefore there is material lacking somewhere. We have maybe sagging of the material, and therefore we have created this digital workflow where basically the second portal of the DBFL is picking up a laser scanner, automatically scans the wall directly after printing, and then in Grasshopper does a cloud compare between the points as they should be and as they are, and based on the differences, automatically a new path is generated that either adds material or subtracts material directly. So there are a couple of iterations of this idea of textile reinforcement. One seminar that we recently held in teaching together with TU Munich, with Katrin Dörfler and Pierluigi D'Acunto, and Mariana Popescu is basically an automation of this computational knitting project. Many of you have probably heard. Mariana Popescu is basically computationally knitting a textile on a computer-controlled knitting machine, and is using this as formwork, and then applies concrete manually to this process, which is again extremely labor-intensive. And hence the idea of this collaboration with 18 students, 6 from Delft, 6 from Munich, and 6 from Braunschweig, was to automate this process and to address this process. So in the first step, students were asked to delve into computational form finding of this textile, to analyze where the forces are, where more material is needed and where less material is needed. Then they went to Delft to computationally knit these textiles on a knitting machine. They were then spanned over bending active reinforcement steel rods, and then in a workshop in Braunschweig, this was installed at the Digital Building Fabrication Laboratory, and there, with the Shotcrete 3D printing method, material was applied in a very thin manner so that this shell could pre-harden to give a kind of a strength through the geometry. And then in the further process, the the reinforcement was added through a kind of again a 3D scanning process where the pins were first detected, then here first the robot would wind reinforcement around the pins, then additional material would be applied, then the surface finishing would be applied, and in the end the corners were cut to precision. In the end, this bridge turned out a little bit thicker than we initially intended, and hence we iterated on this process, also on this process of creating the shape. And this is a process that we call frame winding. Here, a frame is first created in a manual manner. It's basically a steel frame with pins on it. Then the robot would wind around these pins and then apply concrete in a very thin version. And again, here I brought a video of this process. And there's a specialty in this process to prevent the concrete from flying through. So this is a part, again, of a student workshop where we have actually 14 of these elements that create an oval shape as a pavilion. So this fiber winding process, you probably all have seen before, is very similar to the one that Shotcrete is investigating. And then here is this novelty that there's a thin tape layer in between the two reinforcement strands that is applied so that the concrete would be prevented from flying through. So it creates a closed surface, or let's say a semi-closed surface. This tape is available in different porosities, so to say. And then again, as you have seen in the previous process, the concrete is applied in a very thin layer, so that a stiff shell is created. And then again, the subtractive part. So we've also scanned this frame before installing it or after installing it, so we know the precise location, and then the corners are basically cleaned or cut in green state so that a connection is possible to the other elements which would complement this structure. There are some issues, as you can see here, with the material shooting through the tape. This is something that we are currently addressing. So another project that we are investigating is the injection 3D concrete printing. This is basically the attempt to release or deliberate 3D printing from the issue of gravity. And we have kind of three versions of it. One is printing a concrete into a suspension that has similar rheological properties than the concrete itself, so that you can create spatial structures that are not built in layers but in free trajectories. This can be inverted as well, so we can print suspension in a concrete to create porosity, for example. So here we just inserted bubbles of a gel, and which is flowing out later. And also we can print a high-strength concrete into a very low-strength material or isolating material, so that we have kind of an inner skeleton of things where we can address or specifically address loads and supports. So the parameters, this is a project that we are working with the IBMB together. That's the Institute for Materials at TU Braunschweig, and there are a couple of parameters that need to be carefully adjusted, which I can show in the following slide. So basically, the speed is, of course, one crucial issue. If you are too fast, the stream rips. There's nothing new. This is also the case in conventional 3D concrete printing projects. But this one is interesting. If you're going too slow, the material kind of starts curling up, and it creates these these funny curls. Then, of course, we have the problem if the suspension that we are using is not dense enough, the material starts sinking, and only if all these parameters are met, then we are in this window where the delta between the density of the material and the density of the printed suspension is optimal, and where we can create complex nodes and straight lines. So the first experiments, of course, showed that compression structures are working pretty fine with this. Of course, the structures are extremely brittle, and so we did first investigations to print around reinforcement, kind of a pre-installed reinforcement or even a pre-winded reinforcement that is within the suspension, and where we have a special nozzle that encases this reinforcement, and we did some structural tests regarding the embedment of it, and it shows very promising results. But also what is interesting is that we can address structures that are predominantly compression active, dating back to Kuhlmann, who invented the graphic statics, and there are also many research groups working on these principles of graphic statics. They have been applied throughout engineering history, but they are very cumbersome to calculate. You have to draw each vector in space, or let's say here in a plane. So even in 2 dimensions, this is quite labor intensive. If it goes to 3 dimensions, it's becoming even more complex. But with computational tools, of course, this becomes much more easy. So the idea is that the whole structure is always in equilibrium, and that the forces that are acting in one structure are canceling itself out, and therefore you can create very complex structures, spatially, that act in compression only. This is a project of a student group. They were tasked to design a table that acts in compression only, and that they produce in this method. And this is one of these elements of these table legs. The difficulty, of course, is the path planning in this process, because you have so spatially complex elements and you can never cross a path again, right? Because you would destroy what you've created before. So some effort went into finding an ideal path planning for this printing technology. And here they were succeeding. One of these legs, that's another advantage of this production technology, is that you can very rapidly print. So one of these legs is printed in 2 minutes, which is quite fast, and then it rests in the suspension for usually 24 hours, and after that it can be taken out. So this is then also scaled up in a follow-up research project where my PhD student Inan Chao was designing a bridge, or kind of a model of a bridge, a 4-meter span bridge that acts in compression only, and which is then segmented into segments, because we do not have infinitely large vessels to print in, so we rather have small vessels of about a cubic meter to print in. And then we have the supports here, and in the supports the tensional forces are spread, and then there are special connectors 3D printed that you can see here in orange, and these are printed based on a 3D scan. So first all the segments were printed, or maybe I just show the video to it. This is the final structure in the end, and here we have some sequences from the production process. So basically the parts are printed separately in the suspension. They're taken out, then they're 3D scanned, assembled virtually with a little gap in between so that the connector parts can be printed. And then the real thing is assembled. So that's the graphic statics part. And Inan's PhD thesis is about bringing the fabrication constraints and the structural constraints into one design model that all structures that are created are at the same time checked for production feasibility. These are the three parts. This is then the vessel, and initially we used sonographic gel, which decomposes, but it has the advantage that you can actually see the process and calibrate the process. But for the real printing, we use a limestone suspension, which is based on limestone powder, a byproduct, which is very cheap and infinitely reusable. So with the disadvantage, of course, that you don't know what's going on inside. Yeah. You can imagine the frustration the next day when you come back and it's all in pieces. But yeah, so this is the excavation process, and then it's simply just cleaning, scanning, and virtual assembling. Yeah, and then this project continues for another 4 years. This was funded by the Volkswagen Stiftung for 1 year, and now we made a DFG project out of it, and the idea is then the further scaling up of this process and also to test the variations of it. Regarding reuse, I mentioned already that we are looking into predominantly subtractive processes here, but which are now combined into with 3D printing processes. This is a project that was running between ETE and the Digital Design Unit of TU Darmstadt. So the idea here is that we take or scan old structures, which are then cut roughly into pieces in the DBFL, for example, and then which are then computationally assembled into new structures. And here on the left side, we have these steel pockets, which are still fairly standard parts. But now, with combining this with one printing, we are working on other more elegant jointing principles for these structures. So then the last kind of cluster that we are looking into is the recycling approach, where of course one of the biggest disadvantages next to the issue of reinforcement is the aggregate size that can be used in 3D concrete printing. Usually there are tendencies towards larger aggregates, but many of the structures that are being printed are printed with mortar rather than concrete and have a maximum aggregate size of 4 millimeters. So here the idea was that we can use construction debris to incorporate it into new 3D printed structures, and we call this large particle 3D bed printing, and it's basically a combination of Shotcrete printing together with particle bed printing technologies. So again, this was a collaboration with our materials department, IBMB, and the challenge here is to find a sieve curve for the aggregates that allows the concrete to protrude fully, so that there are no voids created in between the layers, so to have a solid structure. And what we used here is 32 and 16 millimeters aggregates, and therefore we can replace a substantial amount of cement that would usually be used with recycled construction debris. And then, of course, the surface is rather rough, right? So, I mean, another advantage is that the material supports this printed structure the entire time, so we could also think of using low cement binders for spraying. But here comes then the secondary process, where the other portal of the DBFL is used to fine cut the surface. So we take off a couple of millimeters in this milling process, which could be done for aesthetic reasons because you get this really nice 3D terrazzo effect on the structure, but also of course, for joining structures, joining building components. Yeah, there's a close-up of the surface that is created after milling. And then we have a whole research stream lately that looks into materials that can be reused many times, and we are looking into traditional earth constructions and trying to bring this to the digital age to make it also more efficient in production, because unfortunately they are extremely labor intensive. And here we are investigating these collaborative processes. This should be a video. Click on it. Sorry, but I think you've seen it before. Yeah, so basically one of the robots is laying out the earth and the other one is compacting it. It has a slipping formwork, so that the formwork is only needed at this very moment where it's compressed, and below that and before that it's compressed anyways, so there's no need for formwork anymore. And then also, of course, spraying concrete, spraying earthen materials. And here it's interesting to us that we can basically use the methodologies and techniques that we've developed for Shotcrete and adapt them to other materials. So basically the processes are more or less identical, but the parameters are different. One major advantage of using digital processes. And then, of course, printing with earth. This is something that we are using a lot with our students because it's also a very pleasant material to work with. There we fabricate things in large scale. And now, lately, we want to go out of the laboratory. And this is also a video that doesn't play, unfortunately. This is there should be our new digital construction site. Maybe we can see it later again. Maybe I can click on something. There was something. Yeah, but it doesn't show. So that's unfortunate. I think you saw a little bit of it before. So the idea is that on the construction side, we of course want to investigate the entire digital chain from design to the operation phase, but concentrate on the production phase on the construction side and have a whole entire network of different actors that work together on the construction side. And these are, this is a collaborative process, a collaboration between these partners here. Markus Gerke from the Institute of Photogrammetry, then Harald Klofte me from Structural Design, Dirk Loke from Materials, and Patrick Schadner from Building Management at TU Braunschweig. And so we have also these components addressed in the entire setup with 3D tracking systems that would allow us to track material streams and construction workflows. We have a mixed reality setup that would involve humans in the construction process, then a 3D printer, which is a cobalt printer, but which is modified in a way that it's not installed yet, that will have a robotic arm as well for assembly processes, and a fifth axis. and also a couple of mobile robots that could work on the construction site together with these other actors. And this is fairly new, and we've only inaugurated it and have done some preliminary tests. Here are the mobile robots. Again, this video is not playing on the right side, where we kind of, as a first step, bring these processes onto the construction site and see how the different machines and different actors can work together in basically seamless digital processes. So many of these processes are and materials are part of the AMC. That's a collaborative research center that our institute is heading under the spokesmanship of Harald Kloft at TU Braunschweig, and which is a collaboration with TU Munich. And there are 3 areas, one focusing on materials and processes, one on simulation and modeling, and one of implementing these technologies into the construction process. And these are the PIs and an email website of the TRR, which you are happily invited to learn more about the processes that we are investigating. And with that, I think I'm a little bit ahead of time, more time for questions, but that will be it from my side. Thank you very much.
So thank you very much for your presentation, Norman. Particularly love that approach using Shotcrete as binder jetting. That was new to me. I haven't seen that yet. And I'm keen to see more of that sooner or later, maybe next year. Questions from the audience? Just raise your hands. Okay. I come from that side.
Thank you very much for the nice presentation. Do you envision collaborating with industry firms to develop your methods?
Yeah, so we are quite diverse in our collaborations. Some of the things that I've shown were predominantly basic research in the DFG-funded collaborative research center, but also we have a couple of collaborations with industry partners where we're trying to bring these technologies that are a little bit more advanced already into industry. So we have collaborations with some material suppliers to also look into other materials that we could shotcrete. Silightment is one of the materials that's a low carbon kind of a cement alternative. With reinforcement manufacturers, with 3D printing startups, and so we would love to see that this more applied, and approach us when you want to collaborate and if you are from industry. Yeah.
Thank you.
I have a question about the structural analysis of these structures, particularly the reuse, the last one where you had this debris bound with concrete. Is it possible to have a structural model of it before you do the actual object and kind of analyze the structural stability? Because that is one of the biggest problems with concrete debris, that you're not able to know the structural stability of the object. And if so, how you tackle the situation?
So, yeah, you're right. So we don't really know what's always in there. So you can. There are some demolition firms that pre-sort that offer concrete debris. This one, there was also plastic parts in there, like old light switches and stuff. And so I guess this wouldn't contribute to the structural stability. So it really depends on what you get as debris, right? So if this is characterized to some degree, That depends on the supplier, but also in this process we did some preliminary samples and then took bore cores and did compression tests to see where we are at with in terms of strength, and then we can use this information to, given that we have the same material then for the real structure, to design our structures.
Thanks for the great presentation, and I think that's following you up from mesh mold to what we have saw today, which is mesmerizing packet of the developments throughout the years. We have saw the conventional way of putting the threads, which are like more related to the construction industry, and also the winding patterns. And from you, I would like to hear where is the potential to delivering it and transfer to the end industry? Where do you see the most potentials? Because it's like the bottleneck of 3D printing in our industry. And I think this insight from you would be very interesting to me.
So yeah, it has a lot to do with existing codes and regulations, and for conventional like layer-based 3D printing, I think the current state of the technology is that you cannot assume it as a structural element, and that it's basically calculated as a lost formwork. And with Shotcrete, we have the advantage that this is regulated in the norms. So basically, we can work with existing norms and could apply it. Now, what we think could be very interesting is in coastal protection, for example. So where we can really use these geometries that we can create, these complex shapes, and we have a research group on that to apply it to urban coastal protection systems. So that would be a pretty direct, let's say, use case. Then in other collaborations, we're looking into how can we apply this technology to buildings that exceed like 3-4 levels, right? That are where we can make more use of 3D printing technologies, because I mean it's questionable if we should 3D print single-family houses, right? Or even using this technique, because it will overperform. We can use maybe other materials or lower performing materials. But these are the two streams that we are looking into, kind of more the infrastructure related things, especially coastal protection and 6 stories plus housing. Yeah.
Okay, any more questions from the audience I've overseen yet? No? All right, then. Thank you for the presentation, and it was a good insight on how powerful such a Transregio project with multilateral universities contributing to a joint research can be, and I think it's a good motivation for more Transregios in the built environment. So hopefully, looking at you two. I want his setup in Darmstadt, but first we need the facilities, and then we need the setup, and I will be gone because they will kick me out after 5 years. Okay, so thank you very much. One applause for Norman. And now we start for a little elongated coffee break, and we meet again at 11 for the deep dive session. So it's time to start with the first session, and I introduce to you Lauren Lacey. She's a Bridge Fellow at ETH in Zurich, where she works as a postdoc since 2020 at Gamazio Cola Research Group. And she did her PhD at the ICD in Stuttgart. And today she's presenting impact printing, which uses a circular material such as excavated earth. And I'm quite keen to see it because I'm one of those clay mud guys myself, and you're throwing mud to print something, and I'm really interested how you do that, because I'm just using basic extrusion processes. So please.
So thanks very much for the invitation. As you said, I'm based at ETH Zurich, but I'm currently in the process of commercializing a research project that we've been developing for 4 years. So impact printing is a new method for additive manufacturing, and the goal is really to enable a really high volume and efficient additive manufacturing method that can not only be economically viable because it's fast, but also that can really move beyond the kind of constraints that we've been faced with by only using industrial robots. So we ultimately wanted to develop this additive manufacturing method for earth-based materials, but to also transfer it from off-site prefabrication to on-site using large-scale autonomous construction machines. So when we began the project 4 years ago, the first thing was to benchmark the kind of criteria that we needed to achieve in order to develop a process that's capable of industrialization. So in order to make something very low cost, we really need to reduce the dependency on skilled labor. We need to really think about efficiency. So in terms of build rate, the target build rate was 1 cubic meter to 2 cubic meters per hour. We need to really also not use custom formwork, and then also keep in mind the embodied CO2 or the greenhouse gas emissions from the processing that is aligned or underneath with the process. So as I mentioned, we wrote this grant in 2020, and we basically there were 3 different chairs involved. So I'm based at Gamazio Cola Research, and Kunal, Ananya, and Victor did a lot of work supporting. Kunal and I worked directly together, and we're doing a spin-off together, which I will present at the end. And we work directly with the Chair of Sustainable Construction, and their expertise is clay-based and alternative materials, as well as life cycle assessments. And the Robotic Systems Lab, you may know them because they're doing autonomous legged robots. So the Animal was a spin-off that came out of their lab, but they're also doing autonomous construction machines. So the autonomous excavator was developed through their lab since the last 10 years. We worked a little bit with WASP to develop some custom hardware. So Max is in the room. We met with them. I can show you a little bit about how we worked with them. And then Eberhard is a local leader in circular supply chains in Switzerland, and they donate a excavated material to us at 0 cost. So first I'm just going to show you the project video. I'm sorry that the audio is not playing, but it's very loud noise. But basically we have a custom mechanism that shoots material with very high velocity. So we're shooting very dense, high yield stress material at about 10 meters per second. And when we do that, basically you can enable a bond between multiple parts. The material is sourced from Eberhard, so it's 75% excavated material. We need very little additives because we already start with a high yield stress. And we've basically mounted and integrated the tool on the prefabrication setup in the RFL to investigate different architectural and structural forms through the MAS teaching. And we've also started to investigate mounting the custom tool also. Oh, sorry, I forgot the order of the video. So through the MAS teaching, we also developed custom surface finishing strategies. So here you can see a robotic process that scans the very textured geometry, and it basically applies a clay-based plaster onto the surfaces after they've been cured. So this is a few weeks after production. And this enables us to achieve a very, let's say, commercially viable surface finish. So as I mentioned, the goal of the project was to transfer our process from on-site to off-site. So we recently integrated our tool on the Menzimuk excavator, And this enabled us to actually build a structure outside the RFL in a kind of semi-structured environment. And this Menzimo can actually hold a tool up to 4,000 kilograms payload, which is a huge opportunity in terms of rethinking material processing strategies from additive manufacturing. So they have also a trajectory following controller that has less than 3 centimeters tolerance. And I'm going to go a little bit into detail about the kind of control strategies that we use on our side for synchronization with the tool. And here you can see a LiDAR that's actually used for the ICP localization of the heap in the map of the external environment. So this was the demonstrator that we just produced. It's about 3 meters tall, and we produced it in 8 days of construction. There are some things that are not fully automated in our process, such as material delivery, but that's something we're working on now. So the main process benefit of this type of additive manufacturing, especially compared to extrusion-based manufacturing, is that we can enable mechanical bonding with materials that are extremely high yield stress, so greater than 28 kilopascals, and they basically wouldn't be able to be pumped. So they're kind of outside the range of delivery from a pumping system, probably even with rheological control. But we don't need that because we can basically take very dense materials and we can precisely control how fast we deposit them. And with this, we can actually deposit material with a high enough yield stress that it already can withstand several meters of vertical buildup. So this is a huge benefit for additive manufacturing because we basically aren't relying on the material, the rapid curing and the rapid green strength development of a material. So now you saw the kind of current state of the research. I want to go backwards and show you kind of the origins of the project. So I began 4 years ago, before we got this ETH grant funding, and we began with a very simple question: is can we project dense material with high velocity, high efficiency, and high accuracy at the full scale? So here are two different, this one's not. Shooting mechanisms, maybe they're not playing, but one is, okay, well anyways, I fast forward. Basically, we started with one belt-based system, which basically would have 2 belts that are rotating continuously. This means that you could enable a very fast cycle time. And we basically upscaled this concept. The target cycle time that I mentioned before is based on a build rate of 1 cubic meter to 2 cubic meters per hour. And so we were basically able to take this 2-belt concept, accelerate parts, and achieve a very high controlled velocity, which we later improved in terms of accuracy. Then there is the question of establishing the yield stress domain. So yield stress is the resistance of a material to deformations, and this is one of the most important material properties to control in terms of 3D printing, because you need to accelerate the yield stress in order to resist plastic failures from the weights above. And what we found in very early experiments is that we can increase the yield stress and shoot at a higher deposition velocity. And this basically means that if you can withstand the yield stress from shooting, you'll also be able to withstand the yield stress from many, many layers of vertical buildup. So basically, we established a kind of relationship that basically we're always aiming to start at greater than 28 kilopascals yield stress. So we had kind of humble beginnings in terms of machine and human interaction. So before we developed all the other parts, we were manually feeding, and we mounted this high payload tool on the z-axis kind of Goodell tower that we have in the RFL. So in terms of hardware, we basically had to develop a modular approach of our hardware for the 2 construction scenarios, both prefabrication and on-site construction. And then we also had to develop a kind of material processing strategy. So in the beginning, we were aiming actually to mount a high payload tool directly to the gantry mount in the RFL. But we realized actually it's quite tricky because of the way the RFL was integrated. So we actually ended up spanning between two different robot mounts and building a bridge structure. And then we took that volumetric massing of our tool and also implemented it on the Menzimuk. So the three subsystems are material delivery, the impact printing tool, and superstructures. And maybe if I go a little bit more into detail, you remember the shooting mechanism. This is coupled with a portioning mechanism, but also basically a batch mixing system and extrusion system. And these are actually earlier versions of the tool because we did patent the tool, and so I'm not showing the kind of final versions. But this is the final hardware, and here you can see it's mounted on the bridge between two industrial robots. So then we took the same massing, and then we built also a large, heavy massing that would protect it and enable it to be also mounted on the autonomous excavator. So I'm going to kind of hurry through some of these other slides, because I think I only have 15 minutes. In terms of software control and integration, we asked ourselves the same question. How do we develop a software architecture that would enable us to easily move the process from being compatible with industrial robot controllers, but also autonomous machines? So our software architecture uses ROS as a high-level middleware, because ROS is the standard, especially in robotics research. And we basically have a high-level controller that's looping through positions, and it's communicating back and forth with a tool controller. And the tool controller is running a state machine, which is basically just looping through states at a really, really high frequency. And then the high-level controller takes the same kind of data structure from the design environment, and then it speaks with either the Menzimuk platform or the ABB robot control software. So one of the big challenges is that we're not approaching extrusion-based 3D printing with a tight synchronization between the material delivery and the robotic system. Actually, when you extrude through a hopper-based strategy, you get actually a decrease in extrusion time. So we developed something to synchronize these two systems, which is based on online linear regression. So as you extrude, if you run at a constant velocity, you'll actually get it'll take longer to extrude. So basically, we predict how long it will extrude with linear regression. And then actually, at the cutting mechanism, we hold the part until it's at its exact moment when it needs to be dispatched. So with this method, we have kind of a desynchronized synchronization. So our robot can move at one speed, and our extruder and cutting mechanism can move at a different speed, but we still enable pretty precise synchronization between those two systems. And then the software for both scenarios looks pretty similar. We basically just have an exporter, which exports very specific information, spatial information about each part, and then also the synchronization data that I mentioned earlier. So the material that we are using, I won't go into too much depth, but I think one of the problems with extrusion-based 3D printing is that you actually have to accelerate the material yield stress with additives. We are using mostly a excavated material that's coming from Eberhard, and we're actually using only a very small percentage of lime. And I'm pretty sure we could actually even minimize it entirely, because we can start in such a kind of stable state with the material. But that means that we're getting very close to an unstabilized earth-based mixture, which means it's fully recyclable. Right now, this mix has around 2 megapascals of compressive strength, but we're currently thinking about other mix designs. How do you vary the granulometry to get better results? And then also, how do you enhance the mechanical properties with surface finishing materials that might have a higher compressive strength? So these are some of the explorations that we did in the context of teaching. This was published this year at Fabricate, so feel free to look into that publication. And we just finished the heap demonstrator in February, and we will publish that shortly, hopefully. So this is the current state of the accuracy that we can achieve with our prefabrication-based approach. This is a huge breakthrough because we produced this in one session, so it's 1.85 meters tall, which you couldn't do with extrusion-based 3D printing in its current state because you would have to pause to accelerate the grain strength. Right now, our cycle time is around 7 seconds per part, but we have only one motor that's driving our whole extrusion system. We're trying to reduce that to around 2 seconds per part. We have a few different optimization strategies, but I think eventually we will be able to match our target's construction rate of 1 cubic meter per hour. And this is really a question of scalability, because if you want to really industrialize process, not only do we have to print fast, but we also have to be able to print high immediately. So that's the main benefit of our process, is that we can immediately build vertically because we already start with a high yield stress. And now it's a question of how fast can we print. So how do we optimize our motor controller, our extrusion system, our control logic, and et cetera. So as I mentioned before, I'm just going to quickly end with our spin-off plans. So we aim to commercialize this technology. And so right now, Kunal and I have been working quite a lot on the business plan and a kind of market entry point. So we plan on entering the prefabrication market. And we have already funding through Bridge, which is one of the big transfer funds in Switzerland. And our concept is to develop a very streamlined-based approach for being very compatible with existing prefabrication-based systems. So to combine, for example, timber with our infill material, and to implement a kind of plug-and-play logic, so all the detailing makes it compatible with other types of prefabrication. So here you can see kind of some of the prototypes that we've been working on. Our method also has a high level of processability because basically we start in a high yield stress, but then we cure slowly. So that means we can wire cut, we can detail, and we can also, as I showed before, we're working on also robotic surface finishing. So here's our product sneak peek. We're still developing these. We're looking for, oh, sorry that the video doesn't play very well. But we aim to incorporate actually quite soon. So I'm happy to hear any feedback. If anyone has any names, suggestions, ChatGPT has not been very helpful on that regard. But yeah, that's the conclusion, and I look forward to discussing with you.
So thank you very much, Laura. Any questions from the audience? I'm starting from the back and coming front.
Hello everyone, my name is Emric from Montreal, Canada. I have a question. I see right now your system seems to be integrated to structures. Are you planning in the future to implement solutions for thermal bridges and to add rebar in the system to make a building itself?
So there's a few strategies for the tensile reinforcement. One, with the prototypes you see on the screen, with the timber, our goal is actually to use the timber as the main load-bearing component so that we can accelerate a product that is easy to do certifications for. So we rely even less on the earth as a, let's say, load-bearing material. Then we can also test fibers in the mixed design. What we're more interested in terms of reinforcement is doing a mesh reinforcement, so looking at glass fiber meshes and then flax fiber meshes, and we're actually going to integrate it into the process. That's our next plan in terms of testing. In terms of really high mechanical, let's say, tensile reinforcement, we do have the benefit that you can basically really process. We're basically milling into the material after we produce. So this is a huge benefit that if we wanted to do tiebacks or you wanted to put something horizontal between the layers, it would be very easy to do that. So this could be, for example, I'm not sure that using steel reinforcement is the right solution, especially because of corrosion. But we do have a lot of process potentials for doing multi-layered structures, for doing tiebacks, for integrating things in the material. And I think the first reinforcement approach is going to be this tensile mesh reinforcement.
Yep, yeah, yeah.
Hey, Lauren, thank you for the talk. I have a very dumb question, I think. Now that you focus on prefabrication, my question is why you print vertical and not horizontal?
I think this is a very good question. I think if you are doing a flat wall, we could test doing printing into a mold or printing flat. Our competitive advantage, especially against other types of printing, is that we can build vertically fast, whereas others can't. So I think it's about also using our method strategically. I mean, prefabrication is the market entry point, but we're still thinking like printing in the building site as just, that's not technically ready enough now. But I think this is a good point, and more than one person has mentioned this. I think the process of lifting it back up, it only works, of course, if it's completely flat, because otherwise when you have any curvature, then that doesn't make any more sense anymore. But.
All right. You had a question.
You mentioned that the ultimate goal is to move the process on-site, and I'm interested, what's the maximum scale of building you envision there? How many stories do you plan to build up with larger hardware to carry the system?
So the Menzimuk can reach, we did a reachability study, and we can reach up to 6 meters. So the hardware limits the scale. I think in terms of buckling stiffness and the mechanical properties, rammed earth structures have been several stories, so and also you build thicker, so you have already a bigger moment of inertia to basically build high. I think 2 stories is basically the maximum that we are pursuing. So we did 3 meters already. I think we could probably do 5 to 6 meters in the next phase. I think now it's about balancing what we develop for commercialization and what also could keep being developed in terms of research. Yeah.
And second related question, for integration with different structural systems, like if you have a timber frame or something, have you investigated non-vertical shots? Because everything you've shown so far, the clay projectile goes straight down.
Yeah.
Is it an option to like diagonally shoot it against the framework or something?
Yeah. Basically, it's kind of tricky because I think when you are shooting with such a high force, I would avoid shooting where you induce a very high shear force in the material. But shooting against something, I think, is smart. I think with the Menzimuk, with the 3-axis gantry system, we don't have orientation control. Yeah. With the Menzimuk, we do have orientation control. And so if we did another Menzimuk demonstrator, we could investigate shooting against angled surfaces, or also doing slight inclinations when it's strategic. Yeah. So that's something to investigate, but I wouldn't shoot at an angle when it's freestanding at such a high velocity.
Yeah. Thank you. It's a really interesting approach.
Anything else from the audience? Yeah.
Thank you. Thank you for the interesting talk. I have a question about the specific advantages of this shooting technology in comparison to stamped clay or Stampflehm. If we're talking about prefabricated elements, probably I've missed the information during the presentation. In this case, I'm sorry, but yeah, thank you.
Stampflehm would need, you mean basically local robotic formwork? Yeah, but then you need formwork, and we only constrain the sides. And we also, so the main benefit is that we don't need formwork, and we're still achieving compaction.
All right, no more questions from the, oh, there is one.
Hi, thanks for the presentation, Lauren, and the novel ideas. When you think about rammed earth, you normally think about something which contains a bit more mass, and the mass is used. So it's kind of a 2-part question. With the prefabricated system you're looking at here, I would ask, how would you foresee
the mass being used? And secondly, so as a thermal mass or et cetera? And secondly, could you also foresee this being used in a infrastructural environment?
Mm-hmm. Once we've optimized our, let's say, material delivery rate, I think it makes, then doing large mass structures, I think is totally feasible. I think there's also possibilities for using our method, 2-layered structures where you then cast on the inside. I think that would be another typology to explore, where you could get huge thickness and mass. Some of the student explorations I didn't show in depth, but there was some columns that were infilled with gravel, or that could, basically the gravel was kind of supporting it on the inside, and then you could also fill it in later. So you could do kind of large, fill in the cavities with any sort of cast material. And then you have kind of a benefit where we still print fast, but then maybe with pouring or with casting, you can achieve even a higher, let's say, volume per time. So I think that's very interesting. I think the thickness of the walls here are only because we start with interior walls, and then we'll also do exterior walls. And so 1 to 2 layered structures. I think we need to figure out how we can have as much geometry control in terms of the thickness. Because when we have a 3-axis system and you have the part that's elliptical, your thickness is kind of constrained. But if you can orient them, you orient by a certain angle to match a certain thickness.
Yeah, he seems happy. Okay, if there's no more questions from the audience, I have a question.
Yeah.
You have a nice system to deploy a lot of material in quite short time, which is one of the weak spots of AM that we all experience in our work. And I usually use functionalization of the components as a justification for doing it with AM. So if I asked you to envision a functionalization you could imply into your work, because what we see here is rather conventional walls and some are bent. But if you could, implement some function for a building, what would you do with this technology, and what would you implement there?
Well, I think it's a question of functionalization, like what functionalization we're discussing. Is it about high resolution? Is it a design intent, or is it aesthetics, or is it actually beneficial in terms of thermal performance, or in terms of ventilation, or I would question whether high resolution systems are always performative, or the main goal is performance. I think with our system, I think there's still a lot of it fills a niche where we can have customization, but with higher throughput eventually. And I think there's still huge customization potentials, even though we're only doing, in terms of commercialization, we're only extruding, so you just have 1 degree of curvature. But we've shown that we can build columns and we can build other types of structures. So I think what performances you're thinking about need to be clarified before I answer further. Because we can also do, we can't do holes in our walls, but we could also do multi-layered structures. Yeah, I think there's a lot of potentials.
Okay, I'm keen to see what the evolution of this project will be. Okay, if there's not any more questions from the audience, we first give applause to Laura. And we move over to Ana Godea. But first, somebody will unplug the computer.
Yes, right.
Did you download the presentation? It's Das ist ja eine gute Frage. Ich habe sie noch gar nicht gesehen.
Is Anna around? Oh, there you are.
Ja, genau, du musst erstmal ein PDF öffnen. Wir können eigentlich Und dann müssen wir noch einen Zoom teilen, damit es auf den Stream kommt. To get the two screens in PDF. No, I don't know. Maybe you just drag it to the other one. Yeah, you can do it like this. And now Control L. And now what? Now Control L. Okay. But I don't.
Okay, that looks about right. So Anna Goidea is a postdoc at EDEC Uni Kassel, and she's working with mycelium. She got a PhD from Lund University in Sweden, and she's a co-founder of the Biodigital Matter Research Group. I guess it's in Uni Kassel too. And she's here to question the top-down design approaches we have in our in our additive manufacturing, and presents a bottom-up approach with a growth-based design from mycelium. And yeah, the stage is yours. Thank you.
Thank you. Thank you. It's nice to be here. Can you hear me? Yes. Okay. So thank you for inviting me and for organizing this. I will, as it was said, I will talk about a different perspective in fabrication, one that is growth-based. Yes, so I was introduced. I'm currently doing my postdoctorate research at EDEC after finishing my PhD at Lund University in Biodigital Matter. So, we've all know this and heard it before, but the current data that we have on the climate crisis brought a lot of attention to the construction industry and the way we're related to the carbon cycling. And besides a lot of different strategies that are needed and applied right now, I think it's really important to reconsider our material culture. And this is because in 2020, the ratio of the anthropogenic mass as it relates to the entire biomass on the planet has already surpassed it. And this is, I think, because it's really hard to conceptualize and to grasp, considering the immensity of the Earth and then how we perceive the infinite natural resources that we have. So in the 1900s, the entire of what we built, like concrete and metals and asphalt and all the processed material on Earth, was 3% of the biomass. And in 2020, it was already higher than it, and in 15 years, it's going to be 3 times as big. So this is just to understand a bit how we're relating and what is our impact as a construction industry to it. Because with this biomass and the role of biology in mind, we can see that since the beginning of humanity, we have been influenced by it and we have been fascinated by it. And even in our early dwellings, in the caves, we've been painting animals, and then throughout in the ancient history, motifs of animals and plants have carried through the acanthus leaf in the Corinthian column, then the Art Nouveau vegetation and Baroque, it's up to the current times where we move from biomorphism, which is just copying in 2D or 3D vegetation or animal biological system to getting inspired from the function. So in biomimetics, these are some examples of biomimetics, we're looking at taking functions from biological structures and applying them into building systems. And while this is interesting and it is a step further, it is far from the potential that we can achieve by really understanding and taking on what biological and natural systems can do into our built environment. And while we've seen examples of large scale, so implementing biological systems at large scale, I think there's a lot of potential in the material systems as well, and especially at all scales. So how do we work with multiple scales, and how do you address these issues at the same time? So this is a concept of transcalarity, which is what I developed during my PhD, which is an organizational principle in complex systems that observes interdependent behaviors between scales. But it is also a design strategy that targets several scales simultaneously while considering their interdependence. So the journey of my PhD started in Namibia, where together with David Andreen, we went to study termite mounds. And this is actually because they're a really amazing example of transcalarity and how behaviors at lots of different scales stack up and create a highly exquisite superorganism that has really impressive function. So we studied the termite mound physiology in two ways, looking at the geometry and function, and then at the materiality. Of course, ideally, these are interconnected, but they just had different focus in two different projects. So the first one is Meristem wall, and here we 3D printed a large, at full scale, a building facade, and this is inspired by the termite mound wall, because it is sometimes believed that the termite mounds act as a thermal, that they modify the thermal environment inside versus the outside. That is not actually the case, but they act as if they are the lungs of a large organism. So to breathe the metabolism of all the termites and that live inside. So in this way, we've also created so instead of being a wall that separates the inside from the outside, it's actually a network of interconnected channels. And these can be actuated with very low volume, with very low energy to move air from the inside to the outside. And it's also integrating different functions inside, such as piping and electricity, so in the typical AM multifunctional, and also opens up to the outside where it can be like a bioreceptive wall for urban biodiversity. And yeah, we also collaborated with Mariana Popescu for the interior CNC membrane that acts as a filter for the channel openings. And this project was exhibited at Venice Biennale. But another way that we looked at this, the functionality and the way we got inspiration from the termite mounds, is the material of it. Because so the termites themselves, they don't have a digestive system that can break down cellulose. So what they do is instead they've made a symbiosis with a species of fungus called Termitomyces, which lives inside the mound. So what happens is that the termites harvest plant matter and bring it inside the termite mound, and here there's a species of fungus that slowly breaks down the material so that both the termites and the fungus can digest and live off of it. And this is why I'm talking about this, is because it's quite an interesting material. It's quite lightweight. It has it's hydrophobic and pretty strong considering how its weight. So we started here to see if we can replicate it and what can we learn from this system. And it is interesting because it is built additively. So the termites added one piece at a time, and how this object in the end, this structure, ends up negotiating a lot of different needs. So the need of the fungus to breathe, so to have access to oxygen, the needs of the termites to access it for deposition and removal, and of course the aggregation of the plant matter. So then what we did, we went to Namibia, as I said, and we opened a termite mound and took samples, lots of samples from inside of it, and then smuggled these samples in a toiletry bag and brought it home in the lab, and then we isolated. And we also managed to get the original fungus that lived inside there. And then we've added the substrate for this, which is plant fibers. In this case, it was cellulose and wood chips, but lots of different substrates are viable. And then we 3D printed with it. So at this stage, this is essentially a wood-based 3D printing, which is in our case, it was a very soft, wet material that on its own didn't really have much stability. But after the 3D printing, there goes a growth stage. And this is where you can see in the middle, the fungus grows on the surface and through the mycelium, which is the root network of it, essentially binds the material together. And what is perhaps even more interesting is that it not only acts as essentially a reinforcement of the wood particles, but it's also changing it at a chemical level. So you can see from the control, our main species that we ended up working with, even after being submerged for 24 hours in water, it doesn't decompose. It maintains its mechanical integrity because it is not just wood pulp anymore. And so we took this material system and put it together in a full-scale 2-meter column to scale up the process. So this project we started in 2017. So it's quite some time ago that we've been trying to address these issues. So I think what's important to get here is that how working with a living organism kind of really forced us to try to address the different scales, because you cannot work at one and then expect it to just solve itself across the different scales. We needed to negotiate the needs of the fungus, which meant increasing the surface area, because we wanted to maximize the enzymes that were secreted by the fungus. Because the more enzymes are secreted, then the higher the transformation rate of the material. And this is why, so understanding what happens at the very small scale, molecular level, down to negotiating. So here you can see how we maximize the surface area so that the fungus has access to oxygen, to breathe during its growth stage, and also this helps for desiccation, so to ensure a more even drying with no crackings or less deformations. And these are some of the parameters that we worked with. So these are spanning the printing parameters, extrusion, to the material composition, to have it both being extrudable, but also biocompatible with the fungus. And then, of course, the design parameters. So all had to be negotiated somehow simultaneously. So to conclude, it is clear that we need of course, lots of different strategies for addressing the current state, but the material rethinking and how the material integrates with the design, I think it's really relevant. Yes, and I think, of course, it's not easy to work through all the scales simultaneously, but I think that now we've reached a point where we can do this, both because of the computational power that we have access to and the tools of fabrication that can materialize these intricate interdependencies that we have. And also, I think it's really important to work across disciplines, because only like this can we bridge the different needs from like very small material scale to global scales of material flows and information. So yes, and this is a project that was already completed. So right now, I've started my postdoc at Kassel just last month. So now we're in the process of scaling up these biomaterials, so testing new different materials, testing different species of fungi and bacteria, and then also we're building a lab that has both the capacity for microbiology and for architectural towards large-scale prototyping. So I think because these interfaces are really important to be able to create these kinds of projects. So yeah, this is where we're at. So stay tuned for the next project. Thank you.
So, hands up.
Thank you. Again, a very interesting approach. I'm curious, how do you envision the longer-term usage of these parts? Does the mycelium continue to grow? Is it sterilized at some point? How do the material properties evolve over time as the ratio between mycelium and wood changes and things like that? Lots of open questions there for me.
Yes, these are very good questions. I don't think there is right now the one answer for it. What we've done in this case is stop the growth by drying and killing the mycelium, which, because even as it is, bringing mycelium into housing raises some issues. So at least if you can say it's inert, this is one way to keep developing and not have too much pushback from users and the industry. But I think there is perhaps there are ways in which the fungus can be kept maybe inactive but still alive. And I think this depends a lot of the conditions of growth and the fungal species. So there's a lot of parameters that need to be discovered and put together. But in this case, it would really help. It would bring even further benefits, such as the capacity to self-repair, right? Like we have examples of concrete with bacteria that when it cracks, it can be regrown. So I think by working, but of course it requires a lot of setup for the microorganism to be able to, that we control it in a way that it doesn't keep breaking it down. But of course, there's also the issues of longevity, and of course this will not last as concrete. So this means that there is a more need of, because it is the potential is that it uses waste and it is very low embodied material requirements, and it is, we're working on making it pretty more easier and less CO2 for growing. But then, of course, it doesn't last as long. So I think another way of looking at an approach is not necessarily making everything last forever, but if it's less cost to make, then we can replace it more often. And then this also comes to issues of care and repair and maintenance around buildings, and there's a lot of things there. But I hope that answers. Sure.
All right, anyone else? Oh, just at the farthest point of the room. You can use your own mic.
I have a quick question about the thickness. So what we saw was a pretty thin layer which is printed. So how scalable is it? How thick can the layers be? And will it have an influence on the drying process and the growth?
Yes, it's a very good question. Well, we started with a thickness that actually came close to the original biological model, which is the fungal comb, because we thought, so the goal was to maximize the amount of fungal growth and the biotransformation. And it was somewhere around 5 millimeters that the growth was maximized on the inside as well. Because in the middle of it, there's almost no oxygen, so therefore there's very minimal growth. But then it can be transported if the thickness is not so high. So this is how we started. But of course, in terms of speed and throughput that it can be done, of course it's highly limited. But we have, on the other hand, right now, the mycelium biocomposites are deployed at quite a large scale through casting. So this is the more common way to produce them, is just to make molds and then cast them. Even in large volumes, they're currently used for like packaging and insulation and things like that. So I think there is a balance to be had between the speed of it and the maximizing the growth and the transformation. But of course, this depends on the use case too. So I think this is why it's actually the possibility for customizing the material properties for the use and for the part that is really high. And of course, there's lots of other different strategies. So we're exploring different ways of 3D printing. So going into binder jetting with it, which kind of has different set of requirements and processes. But yeah, I hope this answered.
All right. One question raises more questions.
Hi, thank you very much. One question idea, like I assume you basically have a pulp and you mix the mycelium into the pulp and then extrude it afterwards. Could you also imagine like to make the mycelium selective, so to say, that you have different areas which have different mycelium content with like different growth rates, so to say, and then also the material changing over time, or like some stuff washing out, for instance, or stuff like that?
Yes, these are very good points. Actually, this is part of what we're planning to do in the next stage, because I think by having a living agent inside the material, I think we can unlock, I believe, like the next level of additive manufacturing, which is actually customizing within. So not just through geometry, but by changing the material properties. And I think there's several ways, by changing the ratio of nutrients, by guiding it, potentially even having stronger, so these are all really potential and really exciting options. But yeah, we're not there yet.
Okay, that was your hand raised?
Thank you. As far as I understood, you took the mycelium that you found originally from the termites and used it here. And I imagine that you did not find only like one stem of mycelium, but different mycelia. And did you also look, or are you planning to look into like a directed evolution where you have an idea of which mycelium you would like to use, or which would be better to use, or do you see?
Yes.
Another
very good question. So we started because the properties of the material of the fungus comb itself, we had samples, and this is really fascinating. And so we tried to replicate that. So this is how the project started. We isolated the fungus, and all the tests were with that. But unfortunately, that didn't end up leading much further, because as much as we could grow it in laboratory conditions, when moving it to larger scale, it didn't really work. And I think in retrospective, it does make sense that it's a 40 million years evolution of this symbiosis between the termites and the fungus. So trying to grow a partner that has evolved without the other one didn't really work. And also there's mycologists that are working on doing this for the purpose of growing the mushrooms, because they're actually a really good apparently they taste really well, and they're quite large. So just from the food perspective, it would be good, and that hasn't been managed yet. So we took it to a step, and then we had to open up the search. So we've done a few other different species that we took in parallel, and then the ones that had the highest speed of growth and the most resistance to contaminants. Because this was also the problem. As much as it would grow, it's a species that has evolved to grow very slowly, so that the termites also have time to eat from the sugars that it breaks down. But then in this case, we don't want in fabrication a fungus that grows very slow. So we spread it out, and we tried a white rot, a brown rot, and a litter decomposer as different strategies to see a bit of the breadth of it. But of course, there's an estimate that there's around, a conservative estimate is that there are 5 million species of fungi in the world. And a lot of the tests that have been done in biomaterials are covering maximum a dozen. So I think there's an incredible opportunity to go through this, because they have such a high different behavior, growth rate, different enzymes that secrete. So I think there's an incredible potential to be discovered still in this field. And yes, the fungal species is actually one of the key aspects.
Okay, thank you very much, Anna. So, time to move over to the last speaker of this session, Andreas Koch. There he is.
Can you tell me if it's the full screen?
Up, so, yeah, no, left, down, up.
Wait, what?
Up, stop. Okay, seems to work. So, Andreas holds a master in mechanical engineering and is now doing his PhD at the Laser Institute of the Hochschule Mittweida. And he's here to present macro SLM for steel. And this is something quite interesting for us as a building industry, because everybody around on this fair is doing micro scale. So you can visit a booth and they will show you a micro isolator for electric devices or whatever. But to be honest, for me as an architect, that's not that much interesting, because I want to build houses, and I can build houses from 2 tiny pieces. So hopefully you have an idea to work this out with macro SLM for steel printing.
Thank you very much for the kind introduction. Yeah, that's exactly what we intend to present to you today. So I guess you can hear me well, right? Good. As we saw before, we had a lot of different materials, but I want to present you metal as a material for 3D printing. And as you can see, we are working in the cubic meter scale, so quite large. And also compared to the other things that you can see on the fair. So we want to work in 1 meter by 2 meter scale, for example. The process that we developed for us is the macro SLM. So some of you will be familiar with selective laser melting, and we just scaled everything up. And in the following 15 minutes, I will present to you who are we, why do we need this new macro SLM process, and how do we use it. And in the end, we will show you 2 use cases of how we and you could implement it in the industry. 2 of my colleagues, Professor Streeck and Martin Erler, are also present if you want to have a chat afterwards. Okay. So we are a public university. We are a University of Applied Sciences in the east of Germany, close to Chemnitz and Dresden. It's a quite small town. And we are having many colleagues who are now for 50 years already are working on many different fields of laser applications. I think not all of you are familiar with laser applications, so I will just give you a brief rundown of what we can do with all the laser technologies. For example, we can have bionic surfaces, we can have macro treatments such as laser welding and so on. We have microprocesses such as laser structuring, as you can see on the left-hand side. Then also we have pulse laser deposition to apply coatings, for example, to steel tools. We have a lot of simulations, measurements, and then bottom left we have additive manufacturing, which is the main part today. Also we have development of digital optics for EUV, for example, biophotonics, and then of course we also build a lot of our laser setups ourselves, so we have a lot of experience on that. So the question is, why do we use a larger process, and why do we need a larger process? The thing is that there's many different applications for this kind of process. I want to explain to you one specific use case. So you can see on the left-hand side a facade that can be custom built with many different angles and so on. And each of those nodes that is connecting the facade has to be usually built by hand, which is a very time-consuming and therefore expensive process. So we were working together with colleagues from Leipzig who are doing the design with a parameterized design of each of those nodes. So they were writing an algorithm that automatically creates all the CAD files for each of those nodes, so thousands of nodes. And we, on the other hand, can then use these files to produce the physical nodes that you can see on the right-hand side. We made a first design study, and we were using the default selective laser melting, as you can see also the machines here on the fair, to print some of those nodes. And you can see it on the right-hand side, it's open, so you can look inside to see the topological structure. And it was still printing 80 hours, and it cost material only, so only the gas and only the powder itself still cost 1,000 euros. And that is first too slow, and it's still too expensive. So we wanted to scale everything up to make it cheaper and faster, while still being able to have all the design freedom of the selective laser melting. So what exactly is the macro SLM process? So I guess some of you will be familiar with the selective laser melting, or SLM. In theory, you can see on the top left, you coat a layer of powder, then you melt it with a laser beam, and then you rinse and repeat for thousands of layers until you have your finished part. In the end, you will also need to do some post-processing, like cutting it and cleaning. And this allows you a very large design freedom, because you have the powder layer that is supporting your structure. So you can print channels, you can print bridges, and you don't have any restrictions regarding the complexity of your design, which is a large advantage. There's also some disadvantages, because usually you will need complex laser scanning devices and so on. And also the powder is very expensive, because it's, let's say, 60 micrometer powder. So you end up with a very expensive process in the end. Also, the build rate is rather low. So if you want to build very high and very wide, we need cheaper processes that are faster. Oh, what's that? Sorry. Was I here? Ah. 1 second, please. Yeah, okay. So a different process that we use to combine with this default SLM is the DEE, the direct energy deposition. Basically, this is a much faster process. And here you don't use a powder bed, which is the largest difference. That means you also use less powder, and you can use much more energy. That leads to a near unlimited size. For example, it's similar to the concrete examples that we saw before. And also very high build rates of up to 1,000 cubic centimeters per hour, compared to the 17 cubic centimeters that we saw before for SLM. But the problem is, as you can see on the top, you always have to build one layer on top of the other, so there is no protective powder bed. So you don't have any of the channels or the more complex geometry that you could build. But as you can see on the bottom right, there you can build very large, for example, tanks for aerospace and so on. And what we wanted to do now is to combine the advantages of both the default SLM, which is the design freedom, with some of the aspects of the direct energy deposition. So for example, we wanted to have an affordable machine with affordable material such as powder. We wanted to have a very high build rate that is comparable with the direct energy deposition. And also we wanted to have large-scale parts. And these aspects together were combined to create a macro SLM. So how do we do that? We still want to keep the powder bed to allow for complex structures. We have a gantry setup, so no optical scanners, so I guess you're all familiar with gantry setups. It's quite a simple and therefore cheap design. Also, we use coarse material, so the material is at least 200 micrometers in powder size, so it's, let's say, 10 times larger than the default SLM powder, and therefore also 10 times cheaper per kilogram. And also we use a single high power laser beam. So there is other approaches with, let's say, 20 or 30 small laser beams that are all acting parallel, but it's very expensive. So we use just one very powerful laser beam. Okay, let's go to our setup. Here you can see the prototype setup that we built at our facility. And what's quite impressive is that it's 2 by 2 by 1 meter of build chamber. So that's many scales larger than the usual SLM machines that you can find. We are having a laser power of up to 8 kilowatts in the continuous wave. And as you can see, we also have the gantry system. So if you look on the picture on the right, you can see my colleague for scale. So it's a very big machine. And the thing is that usually you would lower down the part while it is built. However, that's not possible because if you completely fill this machine, it will be 20 tons of steel powder. So you don't want to move this 20 tons around. Instead, we will move the laser device up. So the machine bed is stationary, while then the recoder and the laser processing head together will move upwards on the 4 parallel Z-axes, and also they are combined with an XY positioning stage. So that's a very simple optical design. We also have very variable spot sizes, and yeah, I think I mentioned all of the important parts. Now I would like to show you the machine in action. Oh, where is this? Is our video? Is there no video? Excuse me, is there a video in this slide? Yeah, just a second, please. No. Well, then I guess it's without video. Okay, maybe I can explain it as such. So you would have seen in the video how the laser machine is moving around, and then the recoder first is applying the powder layer, and then which is about, let's say, 1 millimeter high, so very, very large, and then the laser head is moved by the XYZ axis across the sample to treat a part, and then the next layer is applied, and then the process is repeated. So let's move on to the results that we got. So since we are also a research institute, we want to look very well into the mechanical properties. So how are the structures that we actually build? How reliable are they? And I think you are aware that the most important value for this is the relative density. So how much percentage of the volume is actually filled with metal and not with air or pores or gases, for example, because that would lead to mechanical failure. And in general, we got above the 99.5% threshold, which is the usual threshold. So you could say that we are actually printing completely dense cubes, for example. So you can see on the left-hand side some walls that we printed with different laser powers and different laser sizes. So you can see there that on the left-hand side, 1.8 millimeter walls were printed with 2000 watt of laser power, which for normal SLM would be very much, but for us it's still a low amount. And then we had in the center some 4 kilowatt of laser power, and on the right-hand side of the walls, it's 8 kilowatt of laser power, which is already quite a lot. And you can see there we were able to build 5.5 millimeter wide walls. So basically you could then design your product to be built with, let's say, 5 millimeter walls, and you can imagine how fast that would work. On the right-hand side of the slide, you can see one of the test cubes in the cross-section, so you can see there that it is completely dense, or at least close enough. And with this process, we have a theoretical build rate of 1,300 cubic centimeters per hour, which is more or less also the value that you saw earlier for the direct energy deposition, and about 50 times higher than the default SLM. And for stainless steel, for example, that would be 10 kilograms of stainless steel built per hour. As I mentioned before, the mechanical properties are also very important. And on the left-hand side, you can see the table with the datasheet values from the norm. So we can see that we have to have a tensile strength of at least 500 megapascal. We were measuring 615 megapascal with our tensile probes. And interestingly, also there was no difference between the vertical and the horizontal plane. So there's no anisotropy, which is also very important if you want to apply loads to your samples. The yield strength had to be above 190 megapascal, which was measured at 320, so that was also above the requirement. And the elongation at break had to be at least 25%, but we were having 45%, so it was also ductile enough. So you can say that the mechanical properties of our samples were passing the norm, which is already a very good sign. Also, we did some fatigue tests, and at 1 million load cycles, we had a fatigue strength of about 300 megapascals. Something that is new and not similar to the default SLM is that we have a large degree of design freedom, because as you saw before, we have millimeter-sized walls that we can build up, so they are already very compact and very solid in themselves. On the left-hand side, you can see that we can support different angles. So these are angles that were directly built on top of the powder bed. So you can imagine underneath there was the protective powder bed. And then we could build up to 20 degrees of angles. And that, for example, would not be possible with similar machines as such as the direct energy deposition, because you had no powder bed. Another example in the center is that we can have bridges that are up to 140 millimeter wide, so unsupported, as you can see in the center. So there's one line on the left and one line on the right, and they were combined with these bridges. So there is also another degree of design freedom for you. And one interesting aspect on the right-hand side was the spiral. So there's a center column, and then some millimeters of this column, and then on top there is a freestanding spiral that was built directly onto the powder bed. And that's also only possible because we have such wide area that we are treating with each of the laser beams. And for example, with default SLM, that would not be possible. And for example, you can use this then as a foundation to build on. As you saw earlier, probably, you saw that there's also some oxidation, which is actually normal in most of the additive manufacturing cases. They don't tell you. But then with just some shot peening, shot peening, you could remove the oxide layer. Here you can see my colleague holding the planetary gear for reference, so you can see it's quite large. Here's the same planetary gear. Let's have a look if this video is working. No, it's not. Okay. So you would have seen in this video that the planetary gear is actually moving, and this was printed in one go. So it's not assembled afterwards, it's just printed and cleaned, and then you can already rotate it. So you can actually build rotating large-scale devices with our process. And also here you can see our 10 kilogram macro benchy. I guess most of you are familiar with the benchy. So there you can also see you can build these ramps, you can build bridges, you can build many different structures and still get the benchmark that you wanted. And these, for example, the planetary gear was built in 4 hours, so quite quick. And that had a real build rate of 2.8 kilogram per hour or 350 cubic centimeters per hour. So that's with all the recoating times and so on included. Okay, as I mentioned before, I also want to show you 2 application ideas how we could use this to actually build parts for industry. The first of these would be as a tool. So for example, we can build tools for concrete blocks. Here we are working together in a cooperation with the Cobra Firmen from Germany. So they are the leading producer of concrete molds for on the world. And what they produce is these kind of frames. You have the red frame, and inside you have then steel inlets, and these are produced to treat these concrete blocks with very high forces of up to accelerations of up to 30 G, and then also a high dynamic load, and with very abrasive material. And as you can imagine, for these insets and so on, there's a lot of amount of milling to do. So you actually have to remove much more than half of the material, which is a big waste, since we all want to have less waste. As you can see, there is the tamper head that is applying the forces, and then inside this frame you have some insets. And I will show you one example. We were printing one of these corners of the frame structure, which you can see on the right-hand side. It's about 300 by 300 millimeters. So that's one of our first demonstrator pieces. The main goal was to reduce the waste, as I mentioned, but what's also very important is to reduce the lead time, because sometimes you have casting, for example, as the main method to produce these frames. And then sometimes you have to wait some months for the casting and then still some weeks for the milling, and then it takes a really long time. But if you could 3D print them, it would be much quicker, especially since most of the tools are unique. So every time you have a different tool. We want to reduce the weight. So for example, we could integrate also some curing channels, some weight reducing structures for lightweight. And then, for example, optional design freedom would also allow us to integrate sensors directly into the frame, for example. Here you can see the demonstrator directly after the printing. And then, as you can see, it was shot peened again. And you can see the lightweight structure. So on purpose, we did not close it with a cover layer so you can see inside. Another application would be, again, the nodes that you saw earlier for custom facades. And as we mentioned before, we were printing them with default SLM, but it was way too slow and way too expensive. So our colleagues designed a new version for our very large machine. Maybe you can see it because it's only 2 or 3 lines of the outline. So it's a very rough design that can be printed rapidly. And here in the center, you can see one of our demonstrators. So that's already connected to the rest of the structure. And for example, through the node, you could lead cooling channels, sensors, cables, whatsoever, because you have this additional design freedom. You can also see the very rough structure. So if you would not want it, for example, you could do some milling, some grinding, but it might even be a nice aesthetic aspect. This is about 250 millimeters high. And then on the right-hand side, you can see an example of how you could integrate it into a larger structure. So it's the same design, it's just the default SLM nodes. So you can see out of these structures that are automatically designed and then printed by us, you could build all kinds of custom shades. Now let's come back to the comparison between the standard SLM and the macro SLM. So we saw before that the standard SLM took about 80 hours for one node and about 1,000 euros without any post-processing, so just the steel and just the argon gas, which is very expensive. And with the macro SLM process, we were reducing it from 80 hours down to 5 hours, so you could actually print 2 a day. And then the material cost was down to 150 euros, which is mostly due to the much more affordable powder. On top of that, so that's not including the cost of the machine itself. So on top of that, also the macro SLM machine would be much cheaper than the default SLM machine with all the complicated optics, as I mentioned before. Here on the right-hand side, you can also see that we were printing with 3 millimeters offset, because of course our resolution is not as good as the default SLM. So for example, for the surfaces that actually have a function, you have to include some offset. But since you're printing 16 times faster, that's no problem. And this was also printed with 320 cubic centimeters per hour. We remember here it was about 17, so it's still about 20 times faster. So let's conclude. We built for our process a very large build chamber of up to 2 by 1 cubic meters. The powder that we use is a factor of 10 cheaper, which means that all the products are much cheaper and therefore more affordable. Also, the setup itself is less expensive because it's a simpler design. The build rate is comparable to the direct energy deposition, which is one of the fastest processes to apply metal 3D printing. The design freedom is similar to the SLM. So you can build all the inside structures, the channels, integrate sensors, and so on. We have above 99% of the relative density, so we are printing dense parts. And also our mechanical properties are above the specifications for bulk material. And as I showed you earlier, we have 2 applications, for example, as tools in the concrete production, or for example, directly printing architectural structures such as these nodes. So thank you very much for your attention.
So thank you, Andreas. Questions from the audience? Be careful, he's a mechanical engineer too. The architects won't understand anything.
That's fine. Thanks for your presentation. With your relatively slow gantry and the large spot size, how do you cope with the residual stresses inside the parts?
With what? Sorry.
How do you cope with the residual stresses inside the parts? Because you're using such a large spot and such a slow movement.
Yeah, that's still an issue. So we still are seeing some residual stresses inside the parts, and then sometimes also deformation, but we are planning to use heat treatment, for example, or also we are applying a smart algorithm to produce let's say, to distribute the energy more. So it's not all in one corner of the part.
Okay, thanks. And the other question, how do you shield it from oxygen? Is there any shielding? Because usually you have it like under argon or nitrogen atmosphere?
It's under an argon atmosphere. So it's we are not filling the complete chamber with argon because that's way too expensive, because it's 4 cubic meter. Yeah, it would have been in the video. Unfortunately, it did not show. But below the laser processing head, there's like a hood of argon flow. So it's a local argon atmosphere. So it's not a perfect environment. We are measuring it about, let's say, 0.1% of oxygen still, but it's good enough that you only get light oxidation. Yeah, but it's a big issue, the argon.
Thanks. So, the usual suspects.
Yeah. Some of the glimpses of the software we're seeing look suspiciously like Prusa Slicer or that family of software. Are those actually suitable tool pathing strategies, or is there custom algorithms underneath?
For some parts of our processes, we are using things like Prusa Slicer, yes, but then we are using them. We are connecting them to our custom software and hardware. So, yeah, mostly then we are using complex hardware solutions to treat the signals that they're producing.
Okay, question from my side. Can you do aluminum?
Yes, we can. I did not include it today because due to the limited time, I might have included it in the end. I did not. Yeah, we can do aluminium.
Okay,
Also
you
in
can
the large
do
scale.
also other alloys stuff?
We also tried case hardening steel, for example, so low alloy steel. So we are trying aluminium, low alloy steel, and high alloy steel, such as 3 or 4. Yeah.
Okay, interesting. There's one.
Very nice presentation, thank you. I have a question about industrialization of this process. Who do you think will be the clients? Because right now in 3D printing, everything is quite small scaled, like the metal producers, they're used to a certain range of size, handling, and these type of things. So who do you think will take this technology and bring it to market? Will it be construction companies or welders, or how do you see this?
I think one of the best examples would be tool makers, because as you see, there's quite large tools that are very hard to, or very expensive to manufacture. If you think about forming tools, I don't know, for automotive or things like that. So I think tool makers, for example, could be maybe architecture, but there you might have more norms and.
I can assure you that there are at least 5 to 10 architects in here that want to work with you.
Yeah.
Just because of the scale.
Yeah. That's what we're here for.
Yeah. One last question.
The powder bed you're applying, is it reusable afterwards, or is it getting too hot so it loses its, I don't know, Eigenschaften?
We can recycle it. So sometimes there are larger particles forming, we are sieving them and removing them, and then we can recycle the powder bed to fill the machine again. Yeah, because every time, if you completely fill it up, it's 20 tons of powder, so you don't throw away 20 tons of steel powder every time.
Very good. All right, then thank you very much.
Thank you.
And according to my watch, it's time for the lunch break now. And I have to do some advertising. So we have this book. It's on sale at the front desk for
Great, thank you. Our next session is the Young Researchers section. You will see that actually our researchers in this session are not that young, or rather they are young, but they go forward very fast. So it was initially intended as a session for PhD researchers, but a lot of them actually already defended and have made their way due to the exceptional research that they are about to show you. We are starting with Samim Mendizadeh and Philippe Wüst. Samim is probably the fastest track in our young researchers today, because I think I'm still allowed to say a few weeks ago you were still a PhD researcher at the Digital Design Unit at the TU Darmstadt. And Samim has not only already successfully defended, he's also a junior professor now in Saarbrücken. He presents together with Philippe Wüst, who holds a master's degree in mechanical engineering from the TU Darmstadt and leads the industrial printing group at the Institute of Printing Science and Technology at the TU Darmstadt. And together they will present a presentation that is entitled Multi-Material Hollow Strands by Blow Extrusion 3D Printing, from which I think you can see a few samples in our exhibition as well. Thank you both for being here.
Thank you so much. It's an honor to be still a young researcher for both of us, I think. And today we will present you probably a short portion of our recently started project at TU Darmstadt in the collaboration between two departments, mechanical engineering and digital design unit. And I think that watching out the background, introducing DDU is, I think, not simple, because we know already in this room, but over the last years and during the PhD, I have spent a time at Digital Design Unit, led by Professor Oliver Tessmann, on the hollow constructions and additive methods, which are not directly 3D printing, but actually adding the layers inside the formworks. As you can see, for instance, this robot rotating and distributing the material inside the formwork, or our small research portion on filling the composites between the 3D printed formworks and field material.
Okay, and I'm the one who is new here with our institute, the Institute of Printing Science and Technology. I think it's the first time for the institute and for me as well to present here with architects and from people from the construction industry. So yes, as Samim said, we are from the Department of Mechanical Engineering, and it was usually founded by 7 printing machinery manufacturers, or let's say ink on paper. And these days we are quite large with 5 different research groups and a very diverse team. So we do from embossing in paper to microstructures and 3D printing with living cells or printed electronics, even cultivated meat, quite a diverse range of 2D and 3D printing. And I'm the group leader for the industrial printing, so I focus on everything with conventional printing and 3D printing with plastics.
Yeah, to the problem statement, I think that the material consumption, plastic generally and globally, is increasing, which is obvious for all of us in this room. And now we are consuming 4 times more than 60, 70 years ago. In the future, we would constantly using more plastics. And if you're taking a look at our industry, the building industry and construction, our consumption is also increasing over the last 20 years. Our consumption increased by 5%. Which is quite a high. And I think shortly reported from our industry, as we have heard today, we are pretty lazy and our productivity is not as much as in the rate of the comparison between the other industries. However, the automation sounds to be a promising, which 3D printing is part of this world. And we have also different difficulties by the plastic, which my partner would explain.
And as 3D printing seems like a holy grail to increase productivity, however, it's slow, it's expensive, and there seems to be a lack of innovation in the process itself. And when it comes to large components, there are new difficulties, especially when we're talking about plastics. So the material cost is high, the speed is low, and we need to cool down the plastic parts, and the cooling is usually poor. So our solution is to 3D print with hollow strands. And on the left side, you can see the conventional 3D printing.
where you extrude a solid cross-section of polymer on a build plate, and our approach is to extrude a hollow cross-section, a hollow strand, and we want to expand it using internal pressure. And by inflation with air, we want to create a variable extrusion diameter. So our approach is a highly scalable process with a high volumetric throughput, and we save material by substituting plastic with air, and we have a fast cooling rate as it has thin walls. And this approach of blow extrusion can be solved in two different ways. There are two routes dependent on the feedstock we use. Many from plastics 3D printing know filament-based printing or fused filament fabrication, and we expanded it to fused filament fabrication blow extrusion. And because we use filament as a feedstock, it's easy to process, it's easy to convey, and we can build small, lightweight print heads, so it's interesting for robotic fabrication. And by using different materials, different filaments at once, we can print multi-material parts. However, for the large scale needed here in this, in this scope, we can also use fused granular fabrication, blow extrusion again, and by using pellets as a feedstock, the material is inexpensive and we can have a high material throughput and use the large scale that's necessary for the building construction industry. So we developed two different print heads and each were integrated in a fabrication system. So first of all, we made a fused filament fabrication print head with 4 extruder motors, and the core of the idea is a printed assembly, and I will go deeper in here. So it consists of several parts. Some are just bought, some are custom made, and it mainly consists of a core where 4 different filaments are fed inside, heated up, and extruded through a nozzle. And there is a core inside that leads to the air. I can show you, the air goes just straight through, and the filament is fed through the heat sinks and into the block, heated up, and extruded out. And then we get like a tube. So how does it look like in our 3D printing setup? So first of all, we tried to keep it easy with the one material and try to print a constant diameter. So we're extruding here a hollow structure inflated with some air. And then this seemed to work, so we tried to make it a little bit more complex and 2D printed, actually, it's not 3D printing, with one material and a variable diameter. So, and as you can see, this seems to work as well. So we tried to make it even more complex and go to 3D. And what you can see here is just a sample part. I have it small here, and the larger part is at the beam booth downstairs. And we 3D printed a part approximately 30 centimeters in height with a constant diameter, and then we changed it and changed the diameter. So it's hard to see here, so we made a cut. And on the left side, you can see the constant cross-section, and on the right side, the changing cross-section. And it goes, for example, from 8 millimeter up to 40 millimeters and back. And of course, we did some measurements to verify what we did. And you can see the gray line is the airflow that we requested. And this results in a size of the extruded. And this results in the layer height. And this is the white line. And the white dashed line is what we actually measured. So we are quite close to what we wanted to achieve. So this works with one material, but we raised the complexity even more and tried to print with a couple of materials. Now it's 4 filaments in CMYK colors with a constant diameter and again with a changing diameter. And I think, again, you can see the constant versus the variable cross-section here. And once again, as you can see on the measurements we did, we are quite close to what we wanted to achieve. And the effect is quite mesmerizing when you look at it in a video. So now that the process seems to work, we wanted to implement it into a robotics setup.
Yes, another setup that we have used is specified for the pellets printing, which is also consists of the conventional pellet printing setup with the modified headsets that we have presented within the filament approach. Again, there is air pressure coming in, air goes out throughout the nozzle, and the material can stay out as a hollow tube around it, which is all built because of these elements embedded inside the conventional parts. And again, back to the digital transition and digital workflow, we have started to making a digital workflow which is built from different parts and components from our slicers, and then tools that we can allows us that we are varying the airflow during the printing as well as the other fabrication. And importantly, we started working on the same digital workflow that allows us to change any of these extruder parts and giving us the resilience regardless of our machine and the extrusion and airflow machines as the extension actuators to our robotic setup. We started the challenge of scaling up within two directions of vertical printing and horizontal printing, and target to going to reach the limits of the scalability with the hollow strands, which are like inflating and totally different as the procedures that we know by pressing down the material in the layers over each other. Within this video, in the 6 times more, we started to demonstrating the capacity of the material with the different strands, with the different dimensions. As you can see at this video, we can incrementally changing diameter by manipulating the airflow, or within this video, which I think is very, very more promising on the potentials, we can start with the 20 milliliter per minute, the airflow, starting to increasing the air pressure and the feed ratio, and reaching the different varied interpolated sections of the material. And again, starting to challenge, going through the challenge of watching out how can we take a full control over the parameters of the printing to involve the material flow and the air pressure into our system, to controlling them, and finally getting something that makes us happy and promising that we can transit the digital to the physical workflows, which is in this case not, but it's a very beautiful picture. And in the next prototype series, we are getting closer and closer and closer to our aiming. And I think one very important fact of this interdisciplinary work is that extracting the data during the work and during the procedure allows us to making the feedback loops to see what are exactly the stand of the techniques and how can we implementing those measurements and survey of our prototypes, let's say. But the question is, what can we do with 5 kilograms of the PETG? We can build a cube 15 by 15 by 15, quite packed. We can 3D print it with the 10 millimeters of what we all know, the solid materials. We can go for hollow strands, making it longer, or we can go for hollow strands with variable layer thicknesses. And in our demonstrators, as Philip mentioned, that are here in the exhibition, we have demonstrated that we can scale this system up, which is built in the 2 pieces regard of our working hours and capacity of the robotic reach. And we are looking forward for more implementation of the different functionalities in the industry and bringing these hollow tubes as a capacity for function integration. Another very important outlook, I think, is here. Which,
the outlook is not me, it's the video. But yeah, we can also print with elastic materials and to create flexible or inflatable parts. So somewhere has one here you can touch and squish it if you want to. And now we come to an end of our talk, and thanks to the team and everybody involved. Thanks to Nastasia, she's sitting here. And thanks to TU Darmstadt for the funding, and to our students who did a lot of work and put a lot of effort into this project. Thank you.
Thank you very much. We have time for a couple questions from the audience. Could you please raise your hand? Yep.
Hello, hi. Yeah, one for you, it depends. My first one is I'd like to know, will you share in the future, make public the workflow in using Rhino? The way you actually modulate the air and everything? When you produce, I imagine it's a G code that you made to do that? Or it will be, you intend to share this in the future? And, okay.
Yes, definitely. I think it's a very good question. May I ask you the first question? And then you go for the next one?
Yes, perfect. Yeah.
I think it's very relevant. I mean, we're both from the academic background, and sharing is like the mission of us in the academic world, I think. But I think this workflow is very interesting to publish. If someone is interested, definitely. They're like all based in Grasshopper and Rhino components. And we are now adding more and more the layers of the complexity, because all these different parameters are the variables that need to be somehow jigsaw to each other. But definitely publishing the script is, I like it at least. Whenever it's in the stage that is possible, I mean, it's ready to publish, definitely.
I will really love it. Okay. And okay, thank you very much. A second question, will you apply this technology to the glass, product in the future?
Until now we didn't think about it, but it may be an option because it looks like blowing glass, yeah? So let's see if it's technically feasible. So if you want to fund us, maybe.
How much money?
So we re-invite you in a couple of years to see the glass print. We have time for one more question from the audience. Yep.
I asked so many questions today.
You will have time in the breaks. I'm sorry you are a little bit time bound, but you will have time in the breaks for speakers.
In the examples we've seen so far, you've had a single extrusion. Have you bumped up against any limits regarding the pressurized volume as the pieces get larger? And do you have strategies for sealing off one extrusion volume and starting up another pressurized volume?
Yeah, that's critical. Actually, when we start a print, we just print a line, then we seal it somehow with a screwdriver or something, just put it down, then it's sealed, and then we can start our print. And of course, when we scale it up by inflating even more, there's this one moment when we touch our nozzle, and then it ruptures, and the air goes out, and the print fails. So yeah, that's crucial. And there are some ideas how to seal it for our next print. Like, sounds a little bit awkward, but you can seal it like with the robot, like with a sausage. So you can twist it around, and then it's sealed. But we didn't try it yet, so it's a work in progress.
I have to mention, this is 6 months of development. It's like half a year project. It's like very baby project.
Thank you. Here we go. Emmanuel, are you here somewhere in the room? Because you are next. As soon as I figure out how to do the full screen. Oliver, do you see where is the...
So just like my.
I don't see anything on how to put it full screen. Sorry for the small technical delay. Do you know how to put it full screen?
I don't know.
It's not my laptop. Do you see it? Where? Which one is it? I don't see where that open there. Ja, siehst du das Vollbildmodus?
Da steht Vollbildmodus aus.
Is it here? I don't see it from where I am. Sorry?
Das dritte von unten.
Ach so, hier? So, yeah. Okay, finally. So we keep it young and bright because I have learned today that I think Emmanuel Novak, who is our next presenter, built his first 3D printer when he was something like 12, and he has not stopped since. He is currently a researcher at the Glass Competency Center at the TU Darmstadt. He has kept going with his passion for 3D printing, but he has added glass into the mix. We were talking about doing a little bit of glass printing, hollow glass printing. Not yet, but we are getting to see some glass printing from Emmanuel right now. Thank you for being here.
So thank you very much, Nadja, for this really kind introduction. And welcome to my presentation about enhancing glass plates to 3D printing with glass. Most of the stuff Nadja already said. I'm a civil engineer, and yes, I'm a 3D printing nerd. I'm also doing some glass stuff, but also plastic and geopolymers. And I have also some experience in high temperature processing of glass, like bending and also testing. And also another focus of myself is the structural optimization, which I'll touch on later. To start, I'd like to introduce to you the tree exchange approach of the Glass Competence Center with 3 focal areas. There's the generations, the industry, and the handicraft. And so I will present it to you at the example of spray printing glass. That's the first project I made at the Glass Competence Center. And it starts with the industry. They came to us with a demand for the question. They have a lot of customers. They want to have walls like this or curtains out of glass, something like this. And they asked, why can we spray it? I don't know if here are any glass experts, but yes, it sounds quite stupid. And the physical properties of glass are not suitable for spraying. And also this was the first attempt. It doesn't work. So our head of the Glass Competence Center made a team out of a lot different people, and the youngest one was myself with the age of 19, and the oldest one up to the age of 60. And it was really good to have some guys into the team with no knowledge and an unbiasedness, so you can have myself. I had some stupid ideas, but sometimes it was not that stupid and was integrated into the workflow of this technique. And so we developed a workflow, and it worked after a few attempts to spray print glass. And also crucial was the handicraft. So we had a girl named Maria. She is a glass apparatus builder, something like a glass blower. And it's really crazy. She knows how the flame, which temperature it has. She knows the temperature of the glass, and she knows how to heat it up. So it was really crucial for the parameter tuning. So we had over 40 parameters, and in a fast time, we found the right parameters for these results. I have it also here. So we made translucent parts, we spread translucent parts, also transparent parts, white parts, yellow parts, and red parts, so all colors, and also all sizes. We spread up to a height of 4 centimeters, and also some lower lines, as you can see here. And why this tree exchange approach? From the idea to the results, you just needed 6 months, and below 20,000 years for materials and personnel. So with a few people and a low amount of money, we made some big innovations just because we had some different approaches and the experience from the handicraft. So maybe if you strive to do an innovation on yourself, bring a stupid idea to life, maybe focus on some guys from the handicraft sector or some younger and older people. And for the end of the first part of my presentation, I have some visions what we want to do with this technique in the building industry. So the second part is about glass 3D printing with the FDM process. This process is quite old. So the white picture is from 2015. And what's new this year, we managed to print directly onto glass plates. So this looks like this, or I will give it around. But before working with it, I developed a new test for 2D printed brittle materials. And it's a 4-point banding test with a new geometry. And the first question, just put your hands up. Who thinks that the 90-degree samples on the top left is the strongest one? Who thinks the 0-degree samples? And the 45-degree samples? So it's quite interesting that the 90-degree samples, so the first one, was the strongest one. It's not the layer orientation which matters with glass, it's more the heat treatment. So if you're getting the white heat treatment, as at the top part, the left part, you have a good connection and the layer notches are not decisive. As you can see, the cracks are not going along the layers. And for some comparison, we made the experiment 2 is with the raw material strings. They were a lot smaller, so you need to have some size effect to look at some size effects. But another comparison maybe, so 4mm window glass in the same setup has a mean value of 50 to 90 megapascals. So the strength of the AM glass is suitable for some construction application. What I did is structural optimization of glass plates in the building industry, like on skyscrapers, with topology optimization, shape optimization. And I developed some different designs with some similar performance level. So on the left hand, you can see the material savings in comparison to traditional flat glasses. And for a case study in Frankfurt here, and the material savings are around 60 mass%. And for other bearings and other loads, we get savings up to 70%. Why? Because glass plates, as you can see here, without stiffening structures, which are loaded perpendicular to the area, are quite weak. So we stiffen it to make it bring the loads into the bearings. Another approach for enhancing glass plates is are fixations, which are load guided, or also the interior. So maybe some faucets, or also we made it already, some little shelves, like this one. And also what's also possible for enhancing glass plates, you can see it at the exhibition below, there are some customizations, so patterns or logos and some letters. The most asked question in the Class 2D printing is, are the environmental opportunities? I would say, yeah, there are a lot of environmental opportunities, but only if this process can be integrated into an existing glass manufacturing process like tempering. Otherwise, you need to heat this plate up to over 600 degrees, which is a huge impact on the footprint of this material. So this will be the crucial part in the next year for this technology, to bring it in larger scales and into the industry. Yeah, and that's it. I have to thank you, some guys who helped me in this time, and I'm looking forward to a really interesting discussion with you guys.
Thank you. We have time for 2 questions, and I think we can start right here.
Thanks for your talk. So you showed us these glass panels with increased stiffness. So how much is it because you printed a stringer on top of it, and how much does the stress of the shrinkage, the pre-tension, impact the strength?
So we don't consider the pre-stress. So it's just the stiffening structure we consider in the calculations.
But it should be beneficial as well, right? Or is it the other way around?
So the residual stresses are a more critical point in glass, because you can't control that easily.
So it's like you are tensioning the substrate with the stringer. So this could be beneficial as well, right?
Yeah, I think it's more easier for glass to pre-stress it with temperature. And I think that's the more familiar approach in glass plates, and it's kind of heavy to pre-stress it with the 3D printing process.
Thank you.
Is there any other question? Okay, then we will move on with our next speaker. Thank you very much, Emmanuel. You may have seen, if you have visited our stand, that we have this year a lot more bio-based materials that are being 3D printed and processed. Lisa Heinz will tell us a little bit more about this. She's a diploma designer with a background in product and graphic design and in digital fabrication. She is a research assistant at the Experimental and Digital Design and Construction of the University of Kassel. You might know it by its short name EDEC. It's led by Professor Philip Eversman. And Lisa has been researching wood-based printing there, and especially wood waste. So she is going to show us a little bit more about that. Thank you for being here, Lisa.
So, hello everyone, thank you for having me here today. I'm going to talk about, like Nadia said in her nice introduction, about 3D printing with waste wood, the development of reusable printing material based on waste wood particles, and its digital manufacturing process for wall construction and architecture. My name is Lisa Heinze, as already mentioned, and I'm a research assistant with a training in design at the University in Kassel. And on the behalf of our team, I'm going to present our current results. But first, let's talk about the context of waste wood. On the photo, you see our facility partner, Catch Recycling, where a crane sorts waste wood and places it on a conveyor belt so the shredder can shred it into fibers and it will be cleaned of any contaminants. Here we have an overview of all the waste wood categories, which in Germany are 4. The first one is natural and merely mechanical processed wood. The second includes painted and treated wood. And the third is defined by the use of halogen compounds in the coating. And finally, the fourth one is preservative treated wood. And even after the cleaning process, glass, plastic, and metal may still be present in the fibers, as you can already imagine from the colors of the fibers, especially in A3 and A4. In Germany, 9 million tons of waste wood is accumulated in every year, including industrial and sawmill waste, construction demolition wood, furniture that can no longer be used, packaging waste, and wood from outdoor areas. We have 2 strategies to recycle the wood, the material one and the thermal one, yet only 17% are currently recycled in Germany. Following changes to the Renewable Energy Source Act, thermal recycling is no longer subsidized. However, thermal and material recycling remain equally important. This will change with the forthcoming law in favor of material recycling, which will further accelerate the problem of waste wood recycling. This gives us a good idea where we should think about using waste wood in a circular way. For a better understanding of our current project, I would like to give you a brief insight of our previous one, which focused mainly on the goal of using acoustic panels made from wood waste. The project was called Rethinking Wood, and basically we only used different sizes of wood particles with starch and calcium propionate, which prevents mold. And the fibers are mixed with water and the additives, just to activate the binder, so the used water is quite small amount. And finally, the mixture is put into a mold, any kind of mold basically, and pressed into Here you can see a sandwich element with 2 different sizes of wood particles. The video is a bit nicer with sound, though. The final product is fire retardant and biodegradable, so you can use the material again, and if desired you can mix it with any kind of color and pigment. And for sound absorption properties, the sandwich elements can be improved using CNC milling. So basically to use the finer side to reflect sound and the cursor side to absorb sound. And here are 2 demonstrators of the pattern. And here you can see the finished demonstrator, which plays with the gradient of the particle sizes and surface heights instead of the sandwich elements. And the aim was to create a vision for use as lightweight, fire-resistant, and precisely manufactured insulation and acoustic element. And it could also be used in interior design, model, or furniture mating. And this project gave us an insight into the wood material itself and also established context with the industry partners that we still benefit from today. But now let's talk about the main topic, 3D printing with waste wood. The research can be divided into 2 areas, the technology itself and the material development. And right now our focus is more on the material side. And our research project aims to address 2 key issues, the material, as I mentioned, and the development of a wall construction. The objective is to develop a sustainable alternative through the integration of robotic digital fabrication, and the research aims to create a digital supported process using robotic arms and extrusion technology for the production of sustainable monolithic wall structures. To elevate the different factors which affects the material development, we have created this strategy that scales up in stages. So first, we used manual extrusion to develop a printable material. The second, are benchmark tests in different scales, which are followed by diverse test methods, which I will address later. And in between the 2nd and the 5th step, we are going to develop and design a wall structure, which we are going to finally print in 1-to-1 dimension with probably the help of our industry partner Rupp Gebäudedruck, who is specialized in 3D concrete printing. The material mix we want to develop should have the following properties: moisture resistance, fire retardant, mold resistant, good flowability during print, and should be fast drying. The wood fibers are from the company Jeluwerke, and we are currently using wood flour with a size of 75 micromillimeters, and the formulations with different particular sizes and or fundamentally larger are yet to investigate. Because of the nature of wood, we need some kind of binder, and we used quite a variety, and these are the main 4 we are still investigating today: thiolose, starch, cellulose ether, and chitosan. And once everything is mixed together, we're going to print it, and in our current small setup in the lab, we are using an ABB 6-axis robot with a tool from BASP, a paste screw extruder, sorry, I'm a bit nervous, screw extruder, normally used for clay, and a 5-liter tank with custom-made nozzles. And for the next steps, we are currently developing a low-budget continuous feeding system and a larger extruder. The printed geometries are stored in a drying oven, and water loss is monitored by weighing the samples over time. In order to generate the necessary data, we have developed this categorization system to determine which material formulation can be tested using the usual methods for testing rheology, binding capacity, moisture determination, mechanical properties, fire behavior, millability, or finally, life cycle assessments. As of today, we have tested over 70 different formulations. The results and components tests show that the materials have favorable insulation properties. And at the moment, we are investigating the compressive load. You can see the pre-cut samples on the right. And after this test, we will be able to narrow down the formulation and print them on a small wall segment, as shown on the left side. And the problems we encountered so far are slow drying, cracking in between the layers, as you can see on the photo, huge shrinkage, and poor flowability during printing, which increases print time. The results of the project indicates a favorable outlook for the planned application of a wall construction, whereby generated wastewood is processed through a zero-waste approach into a wall structure with integrated functionalities, including installation management. The objective is to establish a closed life cycle, as illustrated in the accompanying image, from material over 3D printing, use case, recycling, and back to the material itself. The following example illustrates the type of wall structure that is being pursued, and due to the digital manufacturing process, it is possible to design custom cable and power outlets. And in order to improve the insulation even further, you could add, for example, cellulose fibers. And that's it. So thank you for your attention.
Thank you, Lisa. Do we have any questions from the audience? Yes, over there.
Hi. Yeah, thanks for the presentation. Perhaps I missed it, but what binder materials are you using with the wood? What is the actual...
Right now, we're quite in the middle of developing the formulation, but the ones that are have the most potential are chitosan and starch or cellulose ether. So it's a bit of a mixture of them, but we didn't narrow down basically which direction we want to use.
Okay, and the follow-up is because I see you're using the wasp printer.
Yes.
So you treat it like a clay, essentially. The way that it's fed and the way that it comes out and the way that it hardens as well. Yeah.
Yes.
Okay.
Do we have any other questions from the audience? Yes.
Thank you for the presentation. Since you showed the previous project that comes with this beautiful and very controlled surface qualities, I was wondering whether you consider to post-treat the prints if you use them for interior walls to create a certain finish, as we maybe have seen it in Norman Huck's presentation, a kind of post-processing to get rid of the layering relief.
Right now, we haven't thought about post-processing the surface. I think during printing, you can custom the layering, so make it even more aesthetically pleasing. But it's a good idea for investigating that further. But right now, we just started it 1 year ago, so not there yet. But it's a good hint.
Thank you. We now move on to our last speaker of the session, Leo Demont. Leo, thank you for being here. Leo is a R&D engineer and he's manager of the large-scale additive manufacturing workshop at the École des Ponts et Chaussées in Paris. He defended his PhD thesis last year, was entitled Development of a Scale 1 Process for 3D Printing of Concrete with Long Fibers at the Navier Laboratory, which is also part of the École des Ponts. He's an architect by training, has veered away a little bit away from this. And today he's going to talk to us about flow-based pultrusion concrete 3D printing with continuous fiber reinforcement. Thank you for being here.
Thank you so much for the introduction, Nadja. Thank you for inviting me to speak here. Hello, everyone. So my talk is about anisotropic concrete. It's a material that is unidirectionally reinforced for extrusion-based concrete 3D printing, as it's suggested here. And I talk today on the behalf of my colleagues from École Nationale des Ponts et Chaussées, Building Innovation Lab, but also X3, which is one of our industrial partners. Let me say a few words about digital construction at the École Nationale des Ponts et Chaussées. So we are a public institution for training engineers and doing research. So we are concerned about material consumption and environmental impact of the construction industry. That's why we are working on robotics to automate, to improve quality, to have good quality control. We develop also on the right geometry for construction. So this is a large span wood structure where you have like much less steel connections. And at the middle, we do concrete 3D printing. So the background on concrete 3D printing has been really well explained. And I just wanted to make this allusion to my fellow German speaker here, but I don't speak German, so we have the cast-in-place concrete, which is kind of massive bow. We use massive amounts of material, and the process by itself brings this simplicity into bringing a lot of material right. But with the extrusion-based 3D printing, we are more into Flachenkonstruktion, and we are more, it is easier to do surfacic objects. It is easier and natural to do thin things, right? So we'll get back to that afterwards, and we want to have a reinforcement process that makes sense with this idea of surfacic objects. But how do we can reinforce extrusion-based concrete 3D printing? We'll get to the anisotropic concrete, but just a first background element. So we have printing reinforced concrete proposal here from TU Dresden, where they have a robotic system that allows assembling segments of reinforced concrete. We are approaches that are more at the scale of the printed laces, where you are nailing, stapling, unrolling small reinforcement. And we have fiber approaches, where you are integrating fibers in the material. So again, a proposal from TU Dresden that you see, MCF process, which pulls actively fibers, long fibers, and our proposal that we call flow-based pultrusion. This involves very small reinforcement with very thin unidirectional strands of multiple small fibers that are embedded into the printed laces, and that allows us to have a composite material. But how does it work? First, we start with a full large-scale concrete 3D printing system provided by X3, which is big components. You add up some accelerator additive inside. The mortar as the input is very flowable, but thanks to the addition of the additive, you have a phase change. You go from really flowable, and then it becomes really thick. And we use this phase change to both impregnate and pull the fibers passively without any additional motor. It's just due to the flow of the mortar. You have here an illustration. You have the same system, but with the flow-based pultrusion nozzle added that allows to put the fibers inside. And since the mortar stays relatively flowable, at some point it impregnates, and then it thickens, so it can pull the fiber thanks to the flow. Okay, and here's a video of the process. So you see that it's running with the large printer and allows to do quite a large object. For now, this is one of our last prototypes that spans like 2 meters long that I will show you afterwards. And on the left, the right, sorry, you see the carbon roving bundles that are embedded into the multiple laces during the extrusion. So what can we have? So once that we have the reinforced material, is it working or not? So first we did some mechanical tests, just direct tensile tests, sorry. We have 3D printed laces and then we pull them to see how it breaks. If you don't put any reinforcement, it remains elastic and then it breaks in a brittle manner. And that's very normal. And once you have a sufficient volume of fibers embedded, you still have this elastic range that it's not much improved for now. That's kind of the current limitations. But then you enter a ductile behavior, just like reinforced concrete. You have, but then it's a very different mechanics, and you have multi-cracking of your sample. As you see on the image, you have a video of the test where you see the cracks appearing with the color gradient. And at some point, you will have a localized crack opening and the sample will fail, right? But at that point, we have a large improvement of the tensile strength of the material and a ductile failure type, which is good for construction applications. But now, what can we do with this? To discuss that, let's just get back to a typical reinforced concrete beam. So you see the concrete beam here. You have longitudinal steel rebars to retain the bending moments, and you have, sometimes you don't have them, but you have the transverse steel rebar for the shear stresses. And the problem is often you have this mandatory reinforcement volume, and that's a problem with the integration of such technique with into thin elements, right? And thanks to anisotropic concrete and other composite technique, you can propose new systems that are inspired by the old heritage of concrete, but also the newer heritage, I would say, of the composite industry. When you are making thinner and lighter components, here you see that we have aligned the laces into in the direction that puts the right reinforcement in the right direction. So we have fibers aligned in front to retain a bending moment, but we can have transversely printed concrete as well. But also, if you discuss with people from the industry, they will say that the problem with that is you don't have enough mass for the acoustics, but you can certainly put mass in another way with filler material, okay? And you need to, let's say, think composite, as the people from composite likes to say when they describe their structures. But you can do many other things. So we've seen already all the nice ribbed component that Pierre-Louis Guinervy did in the time. We can revisit that. We can also think about trusses, where we have aligned stresses, normal stresses with the rebars. So this prototype isn't reinforced with anisotropic concrete, but it's a first design that we did with a processing system that involves putting supports and then printing laces. And at the very right, we have thin shells. And this is not an arch, it's a shell. And you see that you have some little double curvature, as you see from the profiles. And this is reinforced with the fibers, and that's fine because this shell allows not only to retain distributed stresses, but thanks to the tensile reinforcement, it can also deal with localized loads. And the fibers are aligned in the direction of the main direction of this shell, okay? So thank you very much for your attention. I conclude on that, and thank you.
Thank you, Leo. Do we have any questions from the audience? Yes.
Thanks for your presentation. And you showed us the carbon fiber reinforced printing process. And I'm wondering whether isn't carbon prone to oxidation or some chemical effects with the concrete? Or will it just
you mean
be
the carbon
like
fiber?
glass fibers?
The glass fiber with the glass fibers, you mean?
And you printed with carbon fibers in the video, where it stated
yes,
carbon
fiber. And glass.
So is there
as well.
something happening in between the concrete and the carbon fibers on a long term?
We didn't tested this. Okay. But what we just know is that carbon fibers are well used in reinforcement for concrete already. And yes, you could also have glasses, but for glasses you can have problems due to the alkaline environment, but there are like treatment for that for the glass. And we are still quite open on the definition of what material should be used for reinforcement here.
Thank you.
I didn't get it. Maybe thank you for the presentation. Just how much did you observe if the fibers go from one layer to the other? Because at the moment, normally, if you print it, you still stay within one layer. So, did you see that there's an overlapping of the fibers a bit throughout the layers or not? I'm not sure if I understood it.
I thank you. Thing is that within our process, with 2K process, you are pressing a bit the layers. You are not just depositing the layers, so there might be some, I would say, sagging, and so that would maybe help putting the fibers like moving down, or yes, but from what I've seen, I didn't see so much displacement, right? We are inserting like from 5 to 10 rovings into the laces. This roving, they got impregnated and pulled by the mortar. And then, so inside the printer, they are like in a circular arrangement. And then within the printed laces, it's more like elliptic, but it's not like moving too much.
Thank you, Leo, and thank you everyone for your attention. We will now have a 10-minute breaks before we resume for our last session of the day.
Hey, let's kick off the last session for today, session 3, computational design. And I'm very happy to welcome Klaas de Rijke from Bollinger Grohmann Engineers. And Bollinger Grohmann has a lot of offices all over Europe, and Klaas is heading the one in Paris. Klaas is a Belgian civil engineer and an architect engaged in academia and engineering. He's an associated professor at the ENSA Versailles and the Bartlett School of Architecture in London. He's specialized in structural optimization and parametric design. As the director and partner at Bollinger Grohmann, Klaas leads innovative projects like the Louvre Lens, blending art with advanced engineering. And his teaching and professional work focuses on complex geometry, sustainable practices, digital fabrication, and new technologies. Give a warm welcome to Klaas.
Hi, thank you, Oliver, for the introduction. I'm going to use a little bit of a different, I've seen a lot of nice academic research, and of course I'm working as an academic too, but as I am working as a professional engineer, I will try to give a perspective a little bit of a different direction and a bit of feedback what I encounter in daily practice. I know we try to be early adopters with the office, so that means that we try to really build these things. And I think much of you would like to have your solutions out there in the world. So what we try as structural engineers is try to do that and accompany people with their projects. So it's a lot of different projects, to be honest, so I couldn't focus on just one. But I would say it's to give a little bit of food for discussion with the different people here in the room, and what opportunities and complexities that we encounter mostly with these projects. So we work with a lot of different materials, whether it be timber, glass, or other stuff, and 3D concrete printing. It's mostly concrete printing, of course. We got involved, let's say, 10 years ago, and I will try to focus on a couple of different... Oh. Okay. I'm not digital, apparently.
No, it's our fault. So that people online don't miss your talk, and that we have the recording as well.
So I used the break to inform you that there's a YouTube live stream ongoing, which is live now, but it will stay on YouTube. And after this event, we will chop down this very long stream into single lectures. You will find them on the Beam channel on YouTube, and you can also access them from the Beam website. And we are online, so please continue.
Oh, I should have told my kids, actually, live on YouTube. Amazing. Yeah. I didn't think about it, and they never think of me as being cool, so damn it. I have to... Okay, good things for the future. So I'm going to focus on 4 parts: digital tools, the freedom of form, structural design for 3D printing, and on-site or prefabrication. So what happens is we're always a bit lucky to encounter these very crazy people, like most of you in the room here, and to do some collaboration. So all of these things are, of course, in collaboration, and we're learning each time. So this is with the people from Delft. And we developed ourselves back in the days this parametric program called Caramba. And one of my colleagues was working with people from Delft also to find a tool where we can in real time see the structural performance of what is being printed. So taking the data, learning by that data, and constantly improving if the buckling behavior would be okay. So this is basically what the future for us could hold, that by using these digital tools, that on the fly we could actually see the structural performance of these things. So for me, it's also, as a trained architect, also my hope would be that in the end, the architect gets back the power to do the architecture himself. So you sit in the office and you print immediately from a distance. And there's an automatic update also, whether it works structurally or not. So all the workflow on one platform, the digital platform. And this rapid prototyping, of course, is a fantastic item where this collaboration could exist. And so we try to develop the tools throughout we include it in our daily basis. And I have to admit, this is a student's project in Versailles. We had the COVID, so I thought no better way to explain them how digital things work. So we were teaching them how to use a platform, also the slicers. It's together with Sika. And at the end, basically what happened, my 180 students all made a singular design, bespoke, and Sika delivered it automatically to the school in Versailles, which is a bit weird because it's all in stones. It's in front of the Château de Versailles. So to have these 3D printed columns is a bit weird, but it shows also how it works. They were all working from home in the COVID time, and all of a sudden they have the full control of the full design, which is a promise for me actually for architecture. I hope. For us, of course, as engineers, what I'm more interested in is, of course, by topological optimization, that we could optimize the carbon footprint. And I think there, by doing competitions, such as this one for a 40-meter span bridge, we needed to come up with the shape. And this is, again, it's with our digital tools, but what here the hope or the opportunity for me was present that we tried to optimize as much the shape of the bridge by the 3D printing. So the 3D printed concrete would be structural and would be combined with BSC. BSC is a high-yield concrete, 120 MPa, if I'm not mistaken. So they would work together. It would be singular pieces that are kept together with a pre-stressed cable. So it's a hybrid. It's not a pure solution of 3D printed concrete. But what was very interesting, the state prescribed a process where a university, together with architects, together with the contractor, together with a 3D print company, together with engineers, would set up partially a research program, partially a real project. And this was very interesting. So we're still trying from that experience because we lost the competition and the thing got never built, of course. But from that one, we actually went on from that little experience. And this is sometimes the thing also, you have to keep on doing it. So the competition was in 2016. It was supposed to be for the Olympics. And basically now, at the moment, we are printing in Thailand this bridge with another contractor. And we use the same tools and the same ideas. So we optimize topologically the whole project. So this is a bit research. So what we use is the structural force flow in the bridge. And we try to optimize the 3D processes. So for us, it bears that quality of the freedom of form. Somebody already showed that image on the right from Pierluigi Nervi. And why I come to these days also is to get inspiration and then to try to really do it for reality. So this is a research done at the KET, so at a university in Berlin, with Professor Gengnagel, together with Hen and Sika. And then I found a person crazy enough to try to construct it. So at the moment, we're busy to do this in the north of France. So it's in Valenciennes. And some of the researchers in Berlin are actually helping us. But this is also the advantage to not have these boundaries between the industry and between the academia, of course. So you can just suggest, basically. But it's again to optimize the slabs, the force flow, and to really 3D print these slabs. So it means structural design, and we have tried it much before. Basically what happens, since this was a project 10 years ago, but we got kicked out because we were too crazy, apparently. So no reinforcement, so no fibers. It was also with X3, and then the Prüfingenieur, the controlling engineer, he said we cannot get an insurance for that. And this is where the whole thing stops, basically. And why I'm sometimes out there is to make sure I put my signature and that we don't take an insurance and it all goes onto my name. And this is the beauty sometimes. It works in Switzerland, it doesn't work in France, it doesn't work in Germany, it doesn't work in Belgium. Well, in Belgium it does. And in Thailand it also does, so I just sign and it's fine. But here, so you have to find reasons and ways how to convince people. And this is really, so we need structural design for 3D printing. So for the buckling, instead of putting reinforcement, I just went with geometry. So if you make indentures, you actually play with the form and geometry to make it structurally sound. And I think this is also our task as engineers. So from that project, learning again, we are now building, well, the building is actually almost ready. It's a 3-story building, 3D printed in the north of France with Antoine Mott. I don't think he's here today, but check him out. He's selling robots. So please, he's a very fine guy, and he's selling them worldwide. And he's printing himself his own Cité des Savoirs. And we are on the fly learning, and there's no insurance. So I made an agreement with him. He's printing up to 5,000 square meters in total. And we do it on our own. It's his site, so he takes responsibility and we take responsibility for ourselves. It's nice, actually. And from these, I have another example, and I think it's each time with a new client, we try it out, and I think this is the problem what we faced. We have to prototype a lot ourselves, and we don't have the budget for it. Who's paying for it? You have the same at university level. I have the same in the private. So this was for an industrial hall, and I saw already a little shell in another presentation with the fibers before from Leo, I think. So it's a good idea. I think we should try it out. Because this is the one here we started testing. The client gave up after a while. But each time you construct a bit, you get more knowledge. And you have to get it out, built, I think. And so we need to prototype. Because usually nobody, the Prüfingenieur or the controlling engineer, will not sign off on the project if there's not enough testing being done, but we don't have time for that. And every building is an sich already a prototype. So this is another tryout that we do. I will not go into detail. So this is one that we would like to test, basically, but without fibers. And so the last part I wanted to dedicate is to what we often get as a question: do we print on-site or off-site? Honestly speaking, I don't really have much of an opinion, but it's quite complex to do it off-site. You have much more control over the quality, but you have the reverse, that how do you put the pieces together? So often there's a lot of metal pieces included. You have the structural glues that you can use, but they are not okay for the fire. And on the right, for example, what is this maybe the job of the future? So this is a 3D printed house that we were doing, so 3 stories. And there's only 2 guys sitting there and they watch the screen of a computer. So the robot is busy, and once in a while they have to turn the robot a bit around. And I think for me it has a lot to do with what will we want to do with the workers on site. So how do we, the quality of work, and maybe the quality also of the execution. I think that's a big question that we need to ask ourselves anyway. I think labor is going to be too expensive, or should be already much more expensive. And I think there's a quality and a possibility for us to really gain in that part of our dirty business of building buildings. So, but you see how manual it still becomes. They are putting rebars in it, so it's a triple layered wall filled up with concrete. And I'm not very much a fan of it. I would like to get out much more of the concrete. But still, on-site printing has a lot of problems, a lot of qualities, especially with the temperature, the drying, the aging. So, and there's a lot of cracks also that you need to be careful with. The offsite has all these things that you have with the steel elements, of course. So I'm happy to discuss even afterwards. I think it's just, we're learning all the time with all these projects. And we're lucky also to do them worldwide. So each time it's with a different contractor or with a different person. And I hope anytime soon we can see some more innovative projects also. That's it.
Thank you very much, Klaas de Rijke. And the floor is open for questions. Yes.
Hello, thank you for your speech. Do you have any experience with earth-based materials?
Sorry, what?
Do you have any experience with earth-based materials?
Yes, and also even with the timber, by the way, it's we also tried it already, and the earth-based. So this one here on the left, what is happening, because Antoine Mott, he makes his own robots, and the cement, he's trying out the different providers, of course, and he's trying to get the least expensive material, so it's Sika, Lafarge, whatever. And since he got really upset with them, he's now making his own concrete. And he also wants to reduce the cement factor, of course, in it. And that's where he's trying with argile, with clay, also to... So the idea is that they have a formula at the moment that would reduce already of, I think, 40% the carbon footprint. It's not perfect. We have tried it with regular clay also, and even at the university with students and all this. But I don't see it yet as a... Well, it's a possibility, but I haven't tried really in a building. So that's our next step. Yes.
And do you have information about the mechanic, like the strength of that wall or something?
For this one?
Yeah.
Yes, I mean, we get the data from actually, because this guy is producing himself the things, and he also invented a little machine that is doing, because normally for structural engineers, we need the blocks have a standardized size to be tested, which with 3D concrete doesn't exist. So he has a little machine himself that, let's say, every 5 minutes takes a sample, it gives it in, and by having so many samples, you can see the quality and the difference in quality compared to the reality. So it's a kind of data knowledge that he has, and he sells the machine now also, so you can, it's only these little samples, it goes much faster. And he gives us the strength also. And actually with this one, it was quite easy because it's actually Sika that gave a minimal value, which is no, I shouldn't use that word, but actually they can go up much higher because they only give you 30 MPa or something, or 25. You could go up easily to 80. So, and with Lafarge, it's even the same. So they have the very high yield, but actually they give you low value to be okay with the regulations.
Thank you.
One more question here.
Thank you for a great presentation. What I was wondering is the Caramba system integrated inside the 3D printing logic, or the other way around, like if you can feed the pathways of your printer based on reactions of material properties when it is 3D printed, and if this information is integrated inside a Caramba system. Because
yeah, that's exactly what they tried to set up. I have to admit, I didn't follow it afterwards because it's really Clemens that is working on that in our office. And ideally, we would use it in regular projects, but that's the thing. They are implementing it that you can then change the thickness, fastness of the thing, of course. Yeah.
Thank you for your presentation. I have a question regarding like the off-site 3D printing. Do you have like a preferred modular shape for like doing it and bring it to the site? The second question is about to how extent do you think this process is like recyclable or reusable? So if you like deconstruct it.
For the off-site, right?
Yeah.
I have to admit, the experience we had was not so lucky, to be honest. I think the pieces are not so big, and in the end, the only restraint that you have is really the truck. And then the little crane, and actually the pieces are not so big, and whatever, it becomes a volume. So we optimize the shape for structural reasons, but then you start to cut it up in pieces, and the pieces are not very big. So and to reuse the cement, it's like every concrete at the moment. So it's true, that's not much more developed than that. So carbon footprint, we have to work on it, I guess. Thank you.
Thank you, Klaus. And we move on to the next speaker, which is Hamid. Hamid Hassanzadeh. He's a distinguished architect, an entrepreneur, a researcher, and speaker. Having earned his degree in architectural engineering in 2012, Hamid has since contributed to various architectural projects across multiple regions around the globe. In early 2016, he founded, and I'm pretty sure almost everybody came across that, the parametric architecture platform, initially launching on Instagram with 1.4 million followers these days. Today, parametric architecture is more than that. It stands as a globally renewed hub for parametric computational design and AI lovers, boosting over 20 million monthly interactions, and is also very busy in education these days. So a warm welcome to Hamid.
Yes, that's correct. And how do I move like this?
Yes, you can move it too.
Okay, great. Thank you so much for the invitation, Ulrich and Oliver. Nice organization. So I normally speak for 45 minutes, not used to for 15 minutes. Probably I'll take some of your break time and also a little bit of Carlos's start lecture as well. I hope you stand with me. So the evolution of architecture practice from hand drawing to computational design and AI. So I'm going to give you a bit overview of where did we all started doing drawings and where we headed to and how computation and AI is embedding into architecture. Luckily, the speakers before me, they did the most part of my lecture as well regarding the manufacturing and automation. So I learned so many things as well. So thank you so much for all of them. So my name is Hamid Hasanzadeh. I'm an Iranian architect. I worked as an architect for 10 years, and then I founded PA. And I go talk to architects about the possible futures that the emergence of new technologies are bringing into our practice. I'd like to start the lecture with a quote from Leonardo da Vinci, which says, nature is the source of all true knowledge. She has her own logic, her own laws. She has no effect without cause, nor invention without necessity. And I like this quote because it emphasizes on the importance of nature in solving its own problems, as we have seen on all these lectures before me, how people are truly searching for solutions inspired from nature. I'm going to get back to that point again at the end of the lecture. So this is the world right now. You see it in front of us, full of quite complex geometries, design and built with highly advanced technologies and tools, from smaller scales like products into larger scales of master plans and large buildings with different type of materials. So this lecture is divided into 4 sections: hand drawing, computational design, AI integration, and also I'm going to talk a little bit about PA as well. So the hand drawing era almost started 30,000 years ago when we start drawing on the walls to deliver a message about a threat or a little bit about a possible thing that we can transfer to another humans. Then it goes on until the Egyptian era of 6,000 years ago, where we started developing writings. And it goes on until we have medieval. So if I'm passing too fast, so sorry, because I needed to hide so many slides to fit into the timing, and I'm a little bit nervous about that, so sorry for that. So during the medieval time, we started painting the real world images of the images of real world, and you can see the development of one-point perspective on all of these images. And during Renaissance time, these paintings got more and more realistic. And somewhere close to 15th and 16th century, we had the two-point perspective, which is the emergence of drawings officially entering to architecture. And we started drawing buildings before they get built. We visualize them, we imagine them, and you can see all these great works from Palladio, Brunelleschi, and from 15 and 1600s, clearly showcasing the building before it gets built. And this continued on the 16th, 17th century, and it became an undetachable part of architecture, where we transferred the message through drawings. Until 1940s, 50s, where this is the phase of a new an architectural office that is a lot of architects working or designers working on papers to draw stuff as a tool. So the right side image, it looks like an AI-generated image, but it's not as scary as it looks like. But it's an actual image, and it's a picture taken. But this continued until, in parallel, we developed different type of tools that are emerging into architecture. If we want to start with computational design, the analog computing started almost like 700, 800 years ago with architects like Ali Akbar Isfahani working on car bandies, and also different geometrical explorations to deliver these kind of religious mosques in Iran. Or Antoni Gaudi's hanging chain models are great examples of this, how material computing started to shape and come to architecture. The hanging chain models are the flipped version of the structural models that Antoni Gaudi used to design his fascinating buildings. And this is an example of what he was thinking. This is a kangaroo, which is done quite recently, and it's not exactly the same model, but you can see the simple representation that Antoni Gaudi was trying to do with his buildings. Then Frei Otto, another German engineer and architect who experimented so much with soap bubbles into finding forms that are adaptable and can have quite stable structures. A soap bubble is a soap film is a structure that to stay stable, it tends to reduce its surface. I'm sorry, the video is not playing, and it has audio as well, but it's okay. And you can see that based on all these explorations, how Frei Otto was able to design incredible buildings, structures that he had worked on in 60s and 70s. Did I close the screen? I'm sorry. Can someone help me? I think I clicked to the volume up, but it's gone. Okay, it's there now. Yeah. Okay, let's go. A German pavilion in Montreal, Quebec is a great example of this, and Munich Olympic Center is another example of these material explorations. Luigi Moretti is another Italian architect who invested a lot of his time on designing with multiple parameters. And this is a stadium that never got built, but designed with parametric design is the first example of parametric architecture. And it's he's the owner and the person who coined the term parametric architecture as well. Felix Candella's incredible building designs regarding the thin shell concrete, reinforced concrete, thin shell models with reinforced concrete, which are truly masterpieces of the material computing. 2D drafting era almost started with Ivo Sutherland's sketchpad in 1963, where he was working with different screens to design something on the screen, basic geometries with a unique pen. Because of course, high costs of these softwares, it was not quite easy to adapt into architectural practices and workflows. Pierre Bezier, a French engineer who worked on parametric curves or Bezier curves, if you have worked with 3D modeling softwares like Maya, 3ds Max, even on Rhino, you've seen definitely the Bezier name, Bezier curves, where he used to mathematical relations and formulas to rationalize any curve on the computer environment. And this is a quote from the Raynaud management that they said to him when he invented this. But after the invention of the computers, we went back and used his codes to model those curves in the computer environment. 3D modeling era almost started with Greg Lynn, not with Greg Lynn, but with Columbia University research like Bernard Tschumi, Greg Lynn, Hani Rashid, and a bunch of other guys who were trying to use codings into generating 3D models, and they were trying to rationalize these spaces that they can do. And this is a good example of what Greg Lynn did back then, and also the forms that he generated with Greg Lynn form practice. Frank Gehry is another architect who almost opened the floodgates of using softwares into architecture with his works like Barcelona Fish, where he spoke to CATIA company, bringing someone from CATIA company to his office to 3D model what he was trying to build, in this case, which is a Barcelona fish, and he had a good interest in the fish structures. But after a couple of attempts that he calls CATIA company, they tell him, oh, we're not in the fish business, we're in the bird business. We build airplanes, we don't build fish. So, but after a couple of attempts, he brings someone from CATIA company to his office, and then the rest is the history, creating projects like Bilbao Museum, which is one of the greatest architectures of previous centuries. And you can see the details of these his sketch and the 3D model he was trying to do. Along with all these tools that were emerging from AutoCAD, from Revit, and other softwares that were being developed, design computation era almost started with the software called Grasshopper, which you guys all know about it, which enables architects and designers to make visual scripting on the screen. Instead of coding on Python codes, they would be able to write visual scripts. And this was much easier for them to understand the codes and work with them. And you can see it's in this example, this is a very short video of how without drawing any line or any geometry, you are coding your geometry. And you're creating a space or something like that. And with the emergence of Grasshopper, which was basically in 2007 explicit history, it enabled architects to store data, and they can change all those data or play with all those parameters along the way until the end of the design process. And this became an architect's toolkit to generate forms, and these codes can be getting more complicated and complex than this. And again, for Revit, they developed a software called Dynamo, which does the same work for Revit that Grasshopper does for Rhino, and these codes can get quite complicated and complex as well, and the final outputs are these architectures that we see on the screens with highly complex elements and structures, which is not quite possible to imagine, let alone build them, but we are just using softwares to imagine them and then build them. And these structures have their own sense of beauty as well, which emerged after, since this century, that we got equipped ourselves with more tools in the recent years. Building information modeling emerged when we started using an ecosystem of softwares and together to transfer data, to analyze and optimize those data, to create high quality structures that are more optimized into the nature and the environment. And this led us to also work with engineers and other disciplines simultaneously on different type of files. Structural engineers, mechanical engineers, electrical engineers, and we reached to a point that digital twin creation of the same building got much more important than the building itself at some point. It is as important as the building itself. So we can see all the life cycle of the building in one file and how we can, what we're going to do about the building's materials after the life cycle ends, or how we can make it more efficient, or different kind of analytics that we can monitor in a physical model, in a virtual model. And this created also an ecosystem of different tools, different technologies that we can connect to each other. I can connect my bike to my house and measure the energy consumption of it. I can connect my car to my house, or different things could be connected to each other for more, much better performance. The automation in manufacturing, which all our speakers almost covered it, I'm going to pass it, tools like 3D printing, which allow us to build faster in some points and be built much better, and in some cases much stronger, using different robots and different kind of tools like drones in collaboration with each other to create incredible structures and pavilions, in this case with ICD's explorations and these pavilions that they are doing, or cobots, 3D printing models that are incredible example of this, or icon builds, technologies that they're developing recently. They're quite example, even using earth materials to build houses and structures automated and quite fast, and build even on other planets. If we are able to automate these things, why not to think about building on other planets, on Mars, or on Moon, that in this case with ICON's collaboration with BIG, you can see the good examples. And CNC milling and building with stripes, what are the good ways of exploring and building with the stripes and spatial understanding of the forms, or using different kind of HoloLenses to build those stripes, are all great examples of these tools emerging with our industry. And even at smaller scales, like building chairs and having prototypes and customizes of these chairs, each unique and built differently from each other for each person. And even using virtual reality goggles to design in VR and directly send it to manufacturing, like this chair that has been done with Arturo Tedeschi. So where do we go with AI integration? Actually, what is AI? All the, let's first cover this part. All the advancements in artificial intelligence or computer science is because of the advancements in understanding of the human biology and the developments that we are discovering from human brain. And in this slide that you can see, the neurons are quite similar that what those data scientists or developers are doing with artificial neural networks. Time to time, it's getting us more understanding mistakenly that the AI softwares are like robots that they're gonna kill us or something, which is a wrong representation. And a good example of this, the movie Her, that the character speaks to an AI agent and falls in love with her. And the rest is the movie that you can watch, and quite interesting. Or the book Deep Thought, the book Hitchhiker's Guide to the Galaxy, where Deep Thought is the name of the computer algorithm, which is an AI system, and it does everything for the users which they ask. And these AI systems are not going to be robots sitting next to you working on your tasks, but an algorithm that can do everything for you inside your PC. And the basic versions of these, you have used them in your social media while you're doing search or something, that it suggests you based on your experience. How does it generate images? We're not going to get into much of it. I'm going to skip these. But the first images of an AI system that created was this pose invariance image, where they have been trying to generate a dog image, but it's not a dog image that AI generated. It seems like I can see a dog in here, a lighthouse, a snake in here, which is trying to hallucinate of the text that was written on the system to showcase a dog. It developed quite some time until we saw these kind of art images that are generated via AI, and it won a competition, an art award actually in 2018. And from those points, we have been seeing some of the similar hallucinations that people were trying to explore opportunities by feeding their images into system and getting the same type of images. In this case, Daniel Bolotjan, what they did with Deep Himmelblau, the company called Coop Himmelblau, Wolf Prex's company, they fed a lot of their images into system to get the similar designs as Coop Himmelblau, which was quite successful. And another good example of this is the Zaha Hadid collaboration with Refik Anadol, which they had an early access to DALL-E back then in 2021. And they fed a lot of Zaha Hadid Architects images to receive or to have some images similar to Zaha Hadid Architects designs. And in this case, you can see Zaha Hadid is not there, but they can feed the images and they can get similar designs. So what are some of the tools that are doing these kind of things? Definitely you've worked with Launchbox ML, which is a great tool for panelization or similar kind of functions that it does. Hyper is a good example of a text-to-image, text to 3D model flooring, let's say, where you can type stuff and it will just generate for you different models that you can have. These are the basic levels, I can agree, but these models are getting quite advanced in the last couple of years. And what Jasper Wahlgren is doing with Finch 3D, with all these adaptive plans are incredible. And they have launched this last year, and it's quite working and quite adaptive, and it's amazing for architects. You can see on these examples, for example, you can just feed the system with a unique image and get a similar image if you type like a similar architecture close to that image. If you type, for example, Frank Gehry or Zaha or anybody like that. Generating floor plans like in the architectures platform is quite interesting, which is again quite simple, but they're quite getting advanced. Or Make It as another platform that does work with AI systems to generate floor plans. And imagine these getting into 3D models. Get Floor Plan is another platform that generates images through, generates plans through your sketches. And then there's Midjourney, which you have all worked on. The Midjourney version 3 was quite favored by all architects. Now with Midjourney 6.2, which is quite advanced, and creating high quality renders, which are quite realistic. Or DALL-E 3, Stable Diffusion, ComfyUI, which is being used a lot by architects, and Carlos is going to arrive and give a lecture about it. Quite crazy works that he's generating. It's quite admirable. Kyber for video generation, which is the same hallucinations that I showcased with Refik Anadol's or Daniel Bolotjan's works that could be used for exploration of different type of models actually in architecture. Runway is a good example of it as well. Then imagine that you can have 3D models where you just type a prompt and you get a 3D model of it. OpenAI working on a point E where you can have a point cloud and turn it into three-dimensional meshes where at the end of the day will be a 3D model for you. Or Genie AI working with another AI system that can generate 3D models, creating textures with Ponzo AI. So what is the future of AI in architecture with all these? There's a saying in automotive industry where they say we won't be allowed to drive cars anymore, and we won't even notice or even care. Toby Walsh. So these self-driving cars are growing. Yes, at some point we will, the insurance companies will charge other cars if it's not self-driving, and we will transition to a new type of automotive industry, which is all self-driving. And we won't even care about it, probably. Neil Leach has the same analogy in architecture. We won't be allowed to design buildings anymore, and we won't even notice or even care because the cost of designing with an architect is quite high. If you use AI, probably it's going to be reduced. So I'm not sure if that's true, but what will be the role of an architect and designer with the emergence of all these AI tools? Does this mean game over? Did we create AIs to do our art and literature so we can do the laundry? Are we in the right direction? We created them probably to do our dishes so we can do art and explore literature, writings. Will we be able to win wars or competitions and battles without using any advanced tools? I don't know. But even if we develop all these tools, I think humans love to compete with each other and cheer each other and congratulate each other, who we have the objects that are moving faster than humans, but still we are competing with each other and congratulating that. What are some of the ethical considerations of these? I'm going to pass that section. Sorry, I have to close the lecture. So what are some of the challenges that we can overcome? The circular updates can just solve all these things, access and equity to all these advanced tools, preparing for unseen consequences, incorporating trainings and ethics, and talking about the communicating with other interdisciplinary disciplines would solve all these things, actually. Talking about ethics is very important in the use of AI. I think it should be taught in architecture schools as well. Studying art and literature is quite important as the tools are becoming easier, let's say. It will be very important for us to explore the beauty and to deliver a beautiful structure. Again, even we have the advanced tools, as an architect, we have to deliver beautiful buildings. And if, even with those advancements, if you're not delivering beauty in your designs, it doesn't worth to work on it, actually. These are undermined values that architects sometimes skip it, but you have to give a good experience, even if you are designing with advanced technologies. You have to take care of scale, function, balance, unity, variety, harmony, materials, and all sorts of design principles, even if you're designing with AI. So in the last 6 years, we've been working on parametric architecture. We started from Instagram from 0 followers, and then we reached to 1.4 million followers. And we are world's most renowned avant-garde architectural platform about parametric design, computational tools, and AI. Our main focus is the emergence of new technologies in AEC industry and creative industries. Today, our platform reaches to over 20 million people every month on the internet. We are talking to so many architects, asking about their ideas, how they are using these tools in their practices, in their daily workflows, and sharing it on the internet. We are teaching all these tools online with huge numbers of architects interested on all these tools. And we're teaching so many great topics on parametric design, 3D printing, with at least, for example, some of these studios get 1,000 attendees online live. We do live printing online, and the students get interested. So in countries like Germany, it's quite available, but other countries, it's not quite available, and it's quite new topic. So me as a person who is interested in these stuff, I want to share all these knowledges and democratize all these knowledges and advancements with other people as well. And these are some of the works that students have generated through the last couple of workshops that we did online with great instructors that we're inviting from all these schools and bringing back to democratizing their knowledge as well. So thank you.
Thank you very much for contextualizing additive manufacturing and 3D printing. And you totally have a point. If there's no competence in being able to design something that is worth 3D printing, the whole process doesn't make sense. So in that sense, great to look at this broad palette of design and design opportunities. We have time for one short question. Or you approach Hamid in the coffee break that we will have after the next talk. Thank you very much. So we will now move on to the last talk in this session, and I'm very happy to welcome Jörg Petri. Jörg Petri is the founder and CEO of New Digital Craft. He's a registered architect in Germany, and he gained extensive experience in digital and sustainable design through additive manufacturing. He previously served as a business development manager at BASF, Forward AM. He co-founded NowLab and led research at the TU Braunschweig. Jörg was also an associate architect at UN Studio, overseeing award-winning projects globally. Give a warm welcome to Jörg.
Great. Can you hear me? Yes. So thanks a lot for the invitation, first of all. It's a pleasure for me to speak here today. So a short intro, New Digital Craft. What are we doing? We're combining computational design skills with 3D printing, additive manufacturing, to create building products, new solutions for the built environment. And yeah, that's the focus already embedded in the name. The craftsmanship is something that we focus on to really use the tools to bring craftsmanship, you could say, back on the building side, or to just bring digital craftsmanship on the building side. So both is, for us, a key motivation, and it's always looking at sustainable aspects in that process. I want to start with the Step 2 Nest unit, the cadenza stair. We did in an open innovation project, so this is really only possible, a project to create this at the Nest in open innovation research. So basically, companies from the practice, but also research teams come together and basically bring their knowledge from the field into the project. So we realized this stair designed by ETH Zurich, by Benjamin Dillenburger. I'm not going through the whole list. So what I was responsible, you can read it, it's published as well. I was responsible starting at BASF Forward AM back then. So being responsible for the formwork, so enabling a 3D printed formwork, a solution for this stair. So what is unique about the initial idea was to create a lightweight stair that can be handled by 2 persons, bring it on site, and assemble it on site. So this is clearly possible. And it's post-tensioned then with the refer post-tensioning steel. This is a new technology which also makes it possible to have it very intricate and small connections. You can see that here. So it's not possible with a normal post-tensioning method. It's a new method. And how it works, basically, so through heat, the steel that was here formed in a helix and 3 steel wires that were formed in a helix are heated by electricity. So high voltage heats it, and then when it releases, when it cools down, it actually gets the maximum final strength. So it's a cold memory steel. It's also a startup from the ETH there in the market already. And for sure, you can imagine it wasn't clear until really the last tests we did if the stair would hold the promises that we put into. So in terms of structural performance, but also in terms of this memory steel idea. So there were a lot of new inventions in it, in addition to the formwork that we developed, which I come in a sec. So we did tests at the EMPA. Luckily, this connection with ETH and EMPA and the nest, you probably know the nest, it's very helpful in order to do these tests immediately and without questioning. So this was a great experience. So this step in itself has a 50% weight and material of the normal stair you know. It was a sustainable aspect in the beginning, but due to using a concrete that is also quite, let's say, and not a normal concrete, this becomes more or less equal. So we didn't make it a topic, but it's still valid for sure, and it was an initial idea for the design of the stair. So the wires that you see, the metal is only to prevent people from falling. So it's instead of a handrail, it's not holding the stair. So the stair itself is holding itself. You can see it on the left hand. So this was during the building process, which here it seems almost flying, but it's actually standing on a post at the bottom, and it's connected to the floor slab at the top. And it was pre-assembled and then put into place. And Rock Architects did the design of the unit and also coordinated this whole process on site. So it was very helpful to have them on board as well. And so here you see the formwork, which was really our topic then, our task. So choosing the right material, choosing the right technology to be able to have the resolution and also the form stability you need to actually create these intricate objects and how to combine them, and also how to create, let's say, a surface quality that the client, in this case, the EMPA or the nest wanted. So this is one of the pieces you see. And for sure, we printed. This was first on a smaller printer at BASF back then. So now I'm using the Big Rep 1, which is also part of my production in the studio. And it's only 1 cubic meter. You can say it's for sure for building and construction a small volume, but you can already do a couple of things. So we're also combining the molds. So we print parts and assembling them, because anyway we're using a coating on top, which can be removed and keeps the piece as well not contaminated from the concrete, so you can actually recycle it and bring it back into a closed loop later. So this is clearly a lighthouse project, and it's a unique client. You need to realize it. So for me, it's important to also have building projects or building products that are also used, let's say, in a broader range. And this project came luckily where the client contacted us to use our technology to replace a stonemasonry work. So there were 10 windows to be made. And you can see for sure the production cycle is the same. In this case, we scanned an existing window to get the geometry and use a parametric way to, let's say, bring the point cloud into a buildable geometry, and then printed the formwork and casted it and assembled on site. So the reuse aspect is, in this case, the client wanted to keep the mold because we designed it so that we can replace different parts in the building later when they fall apart. So what you see at the top, so this is, by the way, the scanned part and the detailed part that we took in order to generate the geometry. And you can see at the top floor, these windows are still intact, but already some of the lines are degrading. So they want to use the formwork later also to recast it. So financially, this is interesting. For this client, it was the only way to actually rebuild this first floor. It was 10 windows. So you can say cost-wise, with one window, we are as expensive as a stonemasonry. So the first window after that, the second window is already cost-wise interesting, and we did 10 windows. So for the client, it was able to replace or to, let's say, rebuild the building in itself as it was, or to actually generate the aura of the design. And it was also funded even by the European Union because she was able to, let's say, rebuild a structure in the center of the town instead of building a new building somewhere outside the outskirts of the town. So there's funding, clearly funding for this. So, and I started always looking into what can we do with the concrete. So what are possibilities to get a, let's say, less CO2 impact with the concrete? And I found clearly the geopolymer, which is the alkaline silicate bonded concrete. I will explain a bit more in detail. I hope it's not, I'm not going into super detail, but what you, just to understand what you have to see. So there's the cement concrete and the geopolymer concrete. Cement plus water plus sand and gravel, we all know it. It's the normal cement concrete. The geopolymer basically replaces the binder part. So it replaces the cement part. You also have to add water, but really very, very little, 1%. Plus sand and gravel, you get the geopolymer. And the fact, why do we use it? For sure, we all know the CO2 emissions, especially done by the industry, the building industry, is quite high and really under discussion. And from what my partner of where I get all the mixtures of the geopolymers tell, we are around 70%, 60% less CO2 emission than a cement-based or Portland-based concrete. So these figures, for sure, we will see later. We have to, let's say, test it with an LCA, but it is definitely something because why is this the fact? Because the concrete, or what makes the cement, the concrete, so CO2 intensive is the heating of the material over 1,000 degrees. So you can see even 1,500 degrees over a really long time. And in this process, the CO2 is basically emitting, and also the energy you need to produce is quite intense. So this is replaced with a geopolymer. The geopolymer is more activated in a very lower temperatures on a smaller amount of time. And I'm not going into the full detail, but what is very important to understand is it always has a precursor, a so-called precursor, which is a solid raw matter, which can be fly ash, metakaolin, or a slag sand. So it's actually a rest material of iron production. And the activator, which is in fluid form, a water glass. And For me, the geopolymer wording is a bit misleading because everyone immediately thinks it's a plastic, it's a polymer, but it is not. It's really a mineral-based material. And but just by the fact how it solidifies, which you can see on the right-hand side with the silicon, sodium, and aluminium elements, it has, let's say, structures that we know from polymers. That's why geopolymer, geo is also standing for that it comes from a geological base or a mineral base, so a silicate base. So we're doing tests, and I must say the performance is quite impressive. So we're getting very close to normal concrete, even depending on the mixture we're doing, going into the direction of high-performance concrete, which we actually use for the stair. With short fibers, I didn't mention that. So, but coming to the latest and new project we are doing now, and I'm quite happy about this. So it's an outdoor stool, and it's the first time that we combine now the geopolymer with a biochar. Biochar, to explain briefly, is a method of storing CO2 through a pyrolysis, storing basically natural matter that is already there, that if it would rot outside, it would just create CO2. So you actually capture the CO2 in this coal, in this biocoal. There's biochar, and there's companies who do this, and they offer this product to the industry for, to now store this material. And we will have more details later on the performance in the LCA, but we did a first object, in this case an outdoor furniture, which has 13% of this biochar in it. So that's the mass percentage. So volume percentage is 50%. So we actually put 50% of coal, because it's lightweight, into this object, and this is the one you can see here. So, and it's also not so heavy as normal concrete because of the coal, so I can lift it. Normally I would probably not so easy be possible. You see the coal parts here at the top as well, and for sure we used our formworks, 3D printed formworks, and I'm quite happy about the result. So it's really just also to make a statement that's possible to charge now a building component with this biochar, and to actually get a CO2 footprint that is 0 or maybe even minus. So this is something we are now really investigating on. So we are looking into LCA calculations. And so for this, just to add, being in the principle of what we are changing now in the formulation, we just add the biochar to the geopolymer. So the geopolymer already being very low in the CO2 emission, plus the biochar coming on top. And this project is done in cooperation with the ISMD, with Emanuel Novak. So I would like to come on stage, Emanuel. Thanks for joining.
Thank you, Jörg. I want to explain this chart directly to you because it's highly controversial. And first of all, we're not doing any greenwashing. And second, it's highly complex. So if you want to know a little bit more about it, we can have a quick talk after it. What you can see on the right, this material has a footprint. So the production and also the transport, so the stages A1 to A4, emits CO2, what you can see on the right side. But the biochar gets CO2 certificates as well. What's saying here, it's getting GWP, a global warming potential biogenic, which is highly negative for biochar. So in the European norm 15804, they're saying that the biogenic GWP accounts for the amount of CO2 absorbed from the atmosphere and is bounded throughout the material's lifespan. So with this highly negative biogenic GWP, you can add it together, but at the moment it's not allowed because the norm thinks that after the end of the product, the CO2 evaporates. But the material or the biochar which is bounded in here is stored permanently, so for a geological lifespan. So it will not be emitted after time, and the norm will change in future. So you can maybe not saying it, you cannot say it has a negative impact, but of course you're storing more CO2 than you're emitting with this product. But for more questions, we can talk a little bit in the coffee break.
Yes, thanks, Emmanuel. So that's also from my side, from our side, our talk, and yeah, open to questions.
CO2 negative. Questions here?
Thank you for the presentation. Do I understand it correctly that the stairs are made from cast geopolymer, the steps in the stair?
No.
No, okay.
Sorry, if that would have been misunderstood. So the stair was made from a classic or UPHC, so ultra high performance concrete with metal fibers as a reinforcement. So as you can imagine with this geometry, you cannot place standard rebar. We thought about this for sure. In the top part you could, but we then decided to use the fibers. And this was for sure a challenge first in bringing the concrete into the mold to let's say, distribute it evenly, but also having the strength test that I mentioned. The crack test was luckily positive, so in a way that these fibers were enough, because the design was also form active, so there's a lot of tension, pressure elements, but there was one part which was already clear, which is the, let's say, weak part, and it could withstand. So, and that's also kind of to be seen in the presentation. The 3 projects I showed is breaking it down to coming to a more sustainable way using a material that has hopefully the performance of a maybe even UHPC, but being, let's say, more sustainable in the resources that we're using now.
Thank you.
One more question.
Okay. The geopolymer material, what is it like to work with it? Is it liquid, like concrete in a fresh state? Is it printable?
Yeah, it is actually printable. And the company we work with, they provide for 3D printing, and it's also used. I think it was even shown today that geopolymer is printed. I think ETH is also using it on a couple of projects. So I think it even started with the printing idea, but it gets more and more into different products because it is very convincing. And it is really like a concrete. You can imagine. So the difference of the material matter, the powder, you could say, and the glass as a fluid matter, when you mix it, you first mix it, it's more or less like mixing the cement with the water. And then you add the gravels, you add the sand. And what is to point out, in casting, it's really an advantage because you can put sand and gravel in a huge amount into it, as we could see, because the biochar that we added was really in a gravel form. So this is something you cannot do in printing. So, but on the other hand, the gravel and the sand brings a very positive CO2 footprint, depending on from where you get it, if you get local materials. So this, I think, is still interesting to look at it in terms of should it be casted, should it be printed, and this is anyway our approach. So we always say that if it's better to cast it, for example, the 10 windows, what is my next task to really make a calculation? If we would be able to print it, and we will soon be able to print this directly with the high resolution, is it more feasible or also sustainable to print the 10 or to print one form and cast the 10? So I think this is really a question that will come up in the next years or days.
Jörg Petri, thank you very much for your presentation.
Yes.
We are running slightly late, so we'll have a short break so that Carlos Bagnon has a chance to set up his presentation for the keynote lecture, which will be the closing of the day. And there's new coffee. Okay. So we'll move on in a couple of minutes.
Camera disconnected.
Oh.
So for the last presentation there wasn't
the camera from here?
we can check.
Ich glaube, es lädt gerade runter. Möchtest du mal irgendwo gucken?
Vielleicht kurz gucken. Können wir so nicht öffnen?
Ist ja hier, aber wo ist denn... Ah ja.
Die von mich.
Ja, und dann, genau.
Siehst du, hier ist Video starten. Da ist Kamera ausgemacht worden.
So. Okay. Danke.
Und dieses Ding hier, kann man das ausblenden?
Ich versuche es seit Jahren. Ich habe es irgendwie nie
Es kommt
gefunden.
irgendwie mal und mal kommt es wieder. Aber ja, genau, aber ich kann es irgendwie gerade nicht nach oben schieben. Gut, vielleicht, aber jetzt ist es trotzdem nicht nach ganz oben gegangen. Weißt du, was ich meine? Aber ist egal. Ja, genau,
Ja,
aber
ich hab versucht,
irgendwie.
Steffi, kannst du? Ja.
Das Einzige, was wir machen können, ist, ich glaube, man kann es auf einen anderen Screen ziehen.
Stimmt. Du musst nach links ziehen. Ja, perfekt. Okay.
Ja, gut. Ups.
Sind die runtergeladen jetzt?
Ich glaube schon, aber ich kann nicht mehr sehen, dass ich
Anja, was lädt noch runter? Wir müssen noch ein bisschen warten. Weil wenn ich jetzt rüberziehe, dann stoppt ja das Download, glaube ich. Wir müssen noch warten.
Ja, warte.
Ja. Also es kann sein, dass es 5...
Singapore. It's great you made it all the way to Frankfurt. And Carlos Bagnon is an award-winning architect. He's also a professor at SUTD, which stands for Singapore University of Technology and Design. He's also an author of the book 3D Printing Architecture, Workflows, Applications and Trends. He has taught at many universities, including the MIT, the AA, the EPFL, a recipient of the Singapore's President Design Award. His pioneering work in 3D printing and AI has been exhibited globally, including the Venice Biennale, London Design Museum, and the Triennale de Milano. Give a warm welcome to Carlos, and the floor is yours.
Thank you. Thank you very much. Well, thanks everyone for being here, and it's a pleasure and a real honor to be here, to be back in Frankfurt, and for this fantastic event. And today I'm going to focus my presentation on the domain of 3D printing, digital design. Not going to focus on my recent obsession with AI in design. So I'm going to more focusing on the Air Lab, the architectural research lab that I founded in Singapore in 2016. So one of the motivations that we have to use 3D printing is, or to use digital manufacturing and digital design, is that we have a problem with construction waste, and that happens every year. And we believe that the use of technology, and especially additive manufacturing, can contribute to lower the levels of energy in production, to optimize the construction, and to explore different ways and novel ways to contribute positively to our environment. So in our lab, we pose research questions to solve critical problems and improve our built environment. So one of them was a question that we had from a logistics company, DB Schenker, reached us to my lab with a question. It's like, we have a lot of waste here every year. I want to do something with it. So can we do something with packaging waste? So we started thinking of what could be possible to do, right? And then we started working with these ideas that basically started from a very unusual brief. This is basically what we got. We have cardboard, we have plastic, we have bottles, foam, and basically it's like, well, figure out. Let's imagine something with this waste. So these are our raw materials. So the pallets, bottles, foam, cardboard. And then we started thinking of processes to work these basically materials that we had, to process them. And some of them are working with technologies that are already there for quite some time, and we found creative ways to basically to collect the waste. Basically we went to their place to collect the waste. We did the Zoom cutter for the sections, and then we designed chairs for the cardboard tables. We collected them, and then we started working with simple algorithm that creates a shape, and internally we created a structure that basically holds the weight and creates this kind of prototypes. So we made a number of them. Also with the pallets, we created like a nested geometry that created large-scale tables for dining space that they had. So we did like some nesting algorithms with the grasshopper, simple ones, with our students, and tested the integrity of the table, and that was the result. And we look at basically 3D printing of the main features here. So we got a lot of plastic bottles. So the idea was to upcycle them into large-scale chandeliers. And we developed two strategies. This was part of a research grant we had with NAMIC, which is the National Additive Manufacturing Institute in Singapore. And then we started working with basically geometry that could be printed in our standard 3D printers using PET. And the other one was working with robotic printing. So we work with our unit, our robotic arm, that allows us to print large-scale structures and to explore the expressive way to turn this plastic into appealing designs. The idea is that we're using waste here, and we want to make it appealing. We are used to seeing like really designs coming from waste that are not connecting to people, and the idea was to use design, geometry, to connect with the user. So you can see here the results. This is the prototype that we were working with. Our researcher printing one of these panels is about 1.5 meter tall. It's a bit 25 kilos of plastic upcycled here per piece. So we print them in this fashion. We created this panel that has structural stability, and we connected it in this way, right? So here where you can see 150 kilos of plastic fully upcycled here in this chandelier feature. So this is kind of the central chandelier, and behind in the red wall we start displaying the processes. So this was supposed to be the dining space for the employees, and we turned it into kind of a more of a space in which people can learn about these processes. So we created this central chandelier, and we also created a number of them on the tables. So this is a feature that integrates 440 individual tiles, and those tiles are created fully with parametric design, setting the connection detail for each of the tiles. In the end, we have, I think it's 9 different tiles, because they connect, it's a rib of 9 tiles, and they readily integrate. And also, here we're looking at detailing, right? Working with 3D printing, we can integrate profiles, we can integrate the connectors in a novel way, and all these details are new details. I mean, we're thinking of the geometry, we're thinking of the way that we connect these parts, and we are basically in charge of all these bespoke connection details. You can see here the way that the large-scale chandelier is integrated, and we didn't want to make just a number of objects here. We wanted to create a space. We wanted to create a space that could be, the space itself could inspire the people that goes in, and could inspire as well the employees. We structured the space in 3 bands. The one on the left is the red, more didactic band. The one in the center is the action. The white on the side is more for the high table and having some views. And then we developed the whole concept for them. And the red wall was the red wall for basically to learn from these processes. So we made all these drawings and explanations so people can look at the process and actually enjoy kind of the space, learning something. You can see here images of that space. We work, of course, then at the small scale with the furniture, with the chairs, tweaking IKEA lamps as well. So we had a lot of fun with our students, with researchers, working at different scales. And we involved the employees here. So the DB Schenker employees were the ones assembling the chandeliers. So we ran seminars and workshops for them to learn how to put them together. And that was the process that we follow with them. So this is how the space looks. In the end, there's a number of chandeliers, 5 chandeliers, the red wall, and then we have basically turned this lunchroom space into kind of a space that can transfer and somehow show the values of what is possible to be done with waste. This is us working with them, integrating details for the light. And it has been one of the first spaces in Singapore that was actually integrating these components in a functional way. And then we continue our journey as well in our own campus. So the idea was, can we scale it to maybe 150 square meter surface that could be made of 3D printed tiles that can create relatively complex geometries or smooth geometries out of the tiles. So this is the main space for our university, in the main campus. So we had the opportunity to create an iconic piece for the 10th anniversary of the beginning of our school. And then in the central part, we designed this kind of wave that creates pockets of spaces towards the outside, and inside becomes a bit more immersive, and then we have space inside. And the idea was to create a system whereby we can design those tiles with all the connections and references that allows us to create that shape, and also printed in a farm of printers created by our students. The idea was to get every student with a printer to be able to contribute to making this surface. The idea was to create a relatively large-scale structure that meets the CNC route waffle structure below. And that was done, actually, designed and manufactured in about 3 months. From conception to implementation. It was a really quick design exercise that involved many people. And, well, it was a bit of like a quite complex to address. I mean, in the end, we have about like 3,500 tiles. So we had to print kind of templates for the students to know where to put them. But it's quite impressive, the way that it turned out in such little time. We designed details like for the edge, integrating elements that rigidize, integrating like metal parts to make them strong. And this is how the materiality looks like, allowing people to step in. The central part actually is CNC in wood and blends with the tiles seamlessly. This is the space from the outside. So these pockets, this kind of became a central stage for that space. So just by bending, you create these 4 pockets of spaces, but also people can go inside. There was a very simple geometry, and it turned out quite well. Well, we look at plastic as a problem, and we keep working on this process of using PETG to, in this case, to produce a floating farm. As part of our research with Netatech and NAMIC, we started working on a station. It's a quite domestic station that we started working with to turn the plastic bottles into filament. And with that filament and pellets, we were able to produce these kind of floating farms. So the idea was to create smaller pots instead of bigger ones. That the idea is to avoid blocking the light, and we can deploy them in the water bodies of Singapore, and then produce some food, right? Also, they could contribute to something that could be nice to look at, and it could be in different water reservoirs. We optimize the space for the crops, and then we explore different strategies for the ventilation. Here the challenge is, of course, the sunlight that goes inside, but also the ventilation. We explored 3 different options for the mechanical ventilation or the natural ventilation, and we opted for this one. So that's the resulting shape. Turned out like this, a bit like odd, but we developed some simulations and the airflow, and we thought that this was going to work okay. And this is how it looks from below. This basically consists of 2 parts. One is the platform, the top is the cupola, and we did like a first 3D printed prototype. That was the first version. The second version was to use, because we wanted to test the UV light that goes to the plants, we made a first shell. So we produced a 1:2, 1:3 prototype, printed in our lab, put it together with our epoxy, and just makeshift, but worked. So we deployed it out, and we just put it in the pond. It was working okay, as expected. And then we moved into the 1:1 prototype. For the 1:1 prototype, we had to strengthen the structure, because we had to get a very thin layer, so we get more than 70% of the UV light inside, but at the same time, it needs to be stable. So we work with the lattice structure to go with it, run a number of iterations with the equipment that we had. We were using for this one the big rep that we are all familiar with. We know it very well, like the pros and cons, but I mean, it's a machine that was able to print the volume of 1 by 1 by 1 for us. And we explored different patterns. These are different versions. And then the 1:1 version was achieved. This is how it looks. We put the solar panel on top, and then we had our fan. So we get the ventilation achieved, and it was deployed into the water pond, and yeah, it was working quite okay. So it's a cute piece. I think there's version 1. We are working on version 2 with the same company, and we expect to have some number of units deployed in Singapore as an example of things that you can do with waste, and in this case with PET plastic waste. Concerning waste, we are working with Chanel, and we started working with them to find ideas to upcycle what they have, what they throw. We know they throw a lot of things. So the idea here was to design a device that could be locally manufactured, locally printed, so, and it would be easy to reproduce anywhere. So the idea was to create a device that can integrate the Chanel bottles that they throw after the events or they have discarded from the stores, and we can create chandeliers out of that, and that could be implemented in any store locally. So it's made of a piece that actually is integrated by a number of sectors together, connected internally, and there we have we got upcycled aluminum bars to integrate the new caps and the bottles with the core. We have two options here. Is the one standing, and the other one is like suspended. So the one we have here is the one that we did for their warehouse, and they were actually quite happy. So hopefully we can move forward with the implementation on the stores in the coming year. But one of the motivations that we have in the lab goes beyond maybe the creation of those forms, and we are looking at additive manufacture on performance and expressivity in space frame structures. So we believe that this is a way to go, as reduce the wastage, as also creates, and for us as designers, give us a radical new aesthetics as a result of the process, as a result of the thinking, and also, of course, can unlock free-form design for real. And we're looking at space frame structures at the poly that for us is very interesting, very important. It's very attractive to us from the beginning, and we thought that was a really good use case of application of 3D printing. We're familiarized with the standardized space frame nodes, the mirror systems, that still is kind of quite dominant in this industry. We had the vision to start integrating 3D printing connections to solve the intersection of the bars, so we can unlock freeform, we can solve the geometric discontinuity between parts. The idea was to make it seamless, and also to basically to get kind of a certain learnedness and optimization of the structure that other methods wouldn't allow. It was inspired by a neural network. Our nodes are the ones that are printed, and the bars are going to be standard. That was a clear direction we wanted to print just what is needed here, and then to integrate what is standardized and keep doing that. And definitely inspired by then it was 2009, so we have these examples of amazing optimization of the node design, but we wanted to give a different take to it. So we start testing the idea at different scales and with different functions. So here I'm gonna present 5 designs. This is the open house pavilion. This is the I Like Marina Bay pavilion. This is the Sombra Verde. Here we have the air table and also the air mesh pavilion. These 5 projects help us test the idea with different materials, with different functions, in different contexts, indoor, outdoor, different scales. So we wanted to develop, and not only at one scale or just only serving one function. We were evolving the idea and testing it, learning from that. The first one is the V-Mesh project. It was the seed, the beginning of our journey on working on space frame structures. And here I'm going to show maybe the original drawings with the 3D models that we used then. You can see the number of parts. It's very important, as you know, controlling the data that you're working with, the nodes, the bars, and all the different elements of the system. So to generate the nodes, to generate the geometry in which the bars converge to the center, we created a simple Grasshopper script. This is the version 0.1, if you may, but it's the most easy to understand. So you can see here we have the lines, then we have the nodes, and then we go to the bars. We do a fast iteration where we get the vector stream to a certain scale, a certain length that we define. So we have just a diagrammatic approach of the lines, and then we subtract the lines to the bars. Then we start looking at the geometry in a simple way, and also give us the estimated cost in a rough way at the beginning. We can get the surface that we're gonna print, and typically it's quite accurate, quite on point. So in 3D, we look at the node in a more detailed way. We have the bars, in 3D bars. And then this is the geometry that we create. It's only creating like polygons and convex hull geometry. So what we do is to remove the space for the bars that are defined by 4 points. And then what we do is to create a convex hull that can connect the bars. That gives us a geometry of a very low resolution that when it's smoothed out, creates a very nice transition between bar and nodes. And that can be automated very quickly. And we basically have the connection on the ends and the reference of the numbers. And bounding box, then we orient it in the right direction. And there we go, we have the nodes. So that's the node. It's hollowed, as you can see here. And then we immediately get kind of the range of the nodes, and we can estimate the cost of the pavilion at the beginning, right? We have basically the rates of what is going to be the cost. We can sort them, we can analyze. And then here is important because the geometry itself, if we move a vertex, maybe the branches are going to be narrower or wider, and that determines the shape, and that also determines the cost. Sometimes just moving vertices here and there can reduce the cost, of course. There are other factors involved, but then we can see how we can reduce the size of the nodes by modifying the geometry. This is the first set of nodes that we created using PA12 and binder jetting stainless steel and bronze alloy by then. That's a 4060. And this is the PA nodes. And this is this alloy of bronze and stainless steel. So we had 2 kinds to test. And we started putting it together. And yeah, we were quite happy with the slenderness. It was actually extremely thin, the diameter, and the connection came out quite well. You can see here the implementation on site. And it served as the open house pavilion in 2017. And we had a simple exhibition running through a few weeks. You can see how the nodes were connected in space, and basically the slenderness and the lightness was there. We were quite happy of the performance of the structure. Became kind of this kind of canopy on the central space of the campus. And then the next iteration was to integrate services inside. So since we have the space, since we have an empty space inside the nodes, can we run electronics? Can we run circuits? Can we run water? So the structure could be actually used in a different way. So then we conceived these nodes for a pavilion at Marina Bay in Singapore, where we're integrating not just the structural component, but also there's electronics inside, there's LEDs running through that they will be orchestrated in 3D. And then we created, of course, a 3D model to start working on the optimization of the position of the vertices. 147 nodes were created here with this crystalline geometry, more faceted, and was extremely challenging for us working with 54 circuits running 3-dimensionally in this structure, because we are addressing in total 32,000 LEDs through this structure, especially, so it was a really complex code for us to solve. The structure was developed in our lab, and then we took it to the site, but then we had to work on site, so electronics involved was actually very challenging, but we managed to put it together. And this is the result, where people could interact with the piece, and actually the light was reacting to their presence. And this is the look. We have light inside, and the materiality of the structure was actually very different to any other structure. It can actually react, and the colors and the likeness was perceived by people. You can see also the kind of how people could interact with touch. And then at some point we wanted to test the structural limits of this. So we are, in charge of the calculation, but we wanted to see the limits of this physical construction. So we were actually trying to make it collapse. So 3 of us were, in the end, able to make one of the longest bar buckle, and then the structure fell down, and of course we destroyed the pavilion. Well, we're very used to that, right? We milk something, only is a one-off, and then what do we do with the waste, right? So in our case, we wanted to give it a second life, so we turned the pavilion into a chandelier. So in the National Design Center, we collected all the bars as possible the ones that were not broken, and then we printed a new detail for the light bulbs, and then we created light shining in, and that's the feature of the National Design Center chandelier out of basically the waste that we made of the pavilion at Marina Bay. So the idea was to extend the cycle and continue the design with a different function and a different context. So the chandelier, we put it low so actually people can touch it, and at some point you can put it high so it becomes a nice feature for the space. Also, we wanted to test the idea with different materials. So in this case, we work with bamboo. So like, since we are in a tropical context in Singapore, it's a relevant material for construction. Can we use bamboo as a renewable, fast-growing, and powerful carbon sink? The idea was to work with bamboo in a different way than bundling or connecting bamboos in a traditional way. Can we use 3D printing here as well? And the problem is that all bamboo poles are different, so it's difficult to integrate something that is not regular. So we found the solution just working with a very low-tech scanner, like a 2D scanner. So we cut the bamboo poles to a certain length, and then we register the sections immediately with a script. So what we get is all the scans directly into a database, the 2 ends of each bamboo pole, and that is streamlined from bitmap to vector, and vector to a 3D printer connector. The idea is that we have that flow that basically when we scan is registered and transferred already to a STL file that we can print with a reference. The result is that the piece actually fits perfectly to the shape of the bamboo, and then we're able to confidently go ahead with this node system that we tested before. And for here, we use a bit of bigger printers, but still, in this case, working with PLA of a piece that could be about like 40 by 40 or 30 by 40 cm. So it's relatively big, and each of them probably took about like 5 to 8 days or 9 days to be printed, each piece. We were working with 10 centimeters, 10 millimeters thickness. We developed the system to connect, integrating steel cables instead of some of the bars that were actually running in tension. So we developed a number of components. We did some tensile tests too, so we were confident to go ahead with the solution. And then we started assembling that in the lab, and then we took it to the site. The geometry for this pavilion, we relied again in a tetrahedral topology. So we work with tetrahedrons as the base, and then we adjusted to the site. It started with a regular geometry, and then we moved into a more adjusted geometry, and it's in the kind of this quite nice alleys that we have in Singapore, in back of the shop houses. And then we put it together with our team of researchers and students. To put the canopy together was about like 3 hours. Then mounting the roof took a bit longer. But the detail of the roof was very simple. As you can see here, just a peg on top, and then we have a polycarbonate roof, simple and inexpensive for our budget. So, but we were able to extend kind of the geometry of the bamboo and the tectonic somehow, and the roughness as well, if you may, through these connectors. And we felt that this was kind of a natural way to extend the material. We're working here with PLA, biopolymer materials. So that was the intent, to create a structure that could be easy to assemble. And as a result, we thought of a system that could be actually very easy to put together for affordable structures. And we work with the Archifest and Dynamic team to put it together as a display on an exhibition. And we worked as well with bamboo and the idea of the node, but in this case, stretching the node longitudinally. So we have, instead of a node, we have a trout. So we can create a frame with bamboo poles in which in this case, the bamboo poles are crossed in space. and then the nodes are longer. So with that strategy, we can create a lattice. So that lattice, which is a simple system and very easy to assemble, allows, we work with the farmers to dimension what is the optimal size for them, and we work on integrating the pipes inside of the bamboo pole, so actually it runs inside of the bamboo, and then we have at the end solar cell to pump the water, and this is kind of the result. We have a device that we can install in parks, we can install in any space of social housing in Singapore. People can maintain and can adopt different forms. It can be actually this design, but we can of course adjust the geometry to increase the height or to create a smoother geometry to adapt to a different condition. So this was the prototype that we built for the Singapore Academy. And we went back to maybe high performance materials like steel, and then here we tested the idea at a smaller scale. So here we're looking at the air table. We wanted to go to use stainless steel as the material to work, and the idea was to optimize the geometry and to use a table as a proxy to test that structure. So we wanted to put 200 kilos into 3 points, and the idea was to transfer using a space frame, using 6 millimeter in diameter for the bars. So we run some optimizations. We create the, the geometry, the three-dimensional model, the one you can see here. And basically, you can see the design of the table, where all the components are integrated. After optimization, this is the geometry, which is radially symmetric. So we have, for the 3 legs, actually we have still as well as symmetry here. So we are reducing the number of different nodes. It's a design choice. And then we start working with the prototype. You can see here the bars are extremely thin. We're working at 6 millimeter in diameter. And they're connected using a threaded connection. So we're actually threading in and out. The assembly sequence was crucial for us because we were going to a point in which was very difficult to put the bars together. There's no space. And because we use this strategy, we use the threads, right hand and left hand, so the bar, the nodes and bar, when you are threading one bar, the nodes come together. So theoretically it worked really well, but at some point you have the redundancy of the bars, make it difficult to close, right? We have also space, and with this case, it's not like the plastic bars we had before. This is still is difficult to bend. So we learned from the process that if we want to scale this system, it's difficult to work with this detail for sure. But we were able to troubleshoot and finish the table, and the performance of the table was quite impressive. We are, using less than 15 kilos of structure, and we're supporting more than 200. And the load transfer goes to this like very minute, like small, 3 points, like smaller than a coin, and it tells about the precision and the way that we are able to transfer the loads. It was very, very stable, and we work on the details, the connection with the table. You can see here the close-ups, the connection between some of the bars. You can see it's not fully, tangent because of that problem that I mentioned, but most of the bars were actually looking quite good, and the connection was quite precise. Here you can see the details, the close-ups of the nodes and the bars at that small scale, right? And then it turned out quite okay. In the meantime, we're working on a different project for table as well, testing, using a bit like a kind of AI to optimize the simulations for the force analysis. The idea was to test the flow of forces and to transfer that into a geometry. So for the table leg in this case, we're working with a geometry that was driven by the forces themselves, and we work with voxeljet to work on the creation of the ceramic molds to use to create these kind of bronze legs that are manufactured with this complexity. So the geometry is basically what we got from the optimization process. So those elements are force driven. And this was we're here trying to explore the aesthetics resulting from the process. We work with the bronze, we polish it. We have the 3 different legs as we put the table with a non-symmetric condition. And this is kind of the result that we got. We got to learn a lot with the process. We worked with VoxelJet to manufacture the legs actually here in Germany, and the result was quite good. It's kind of the first time we worked with this technology ourselves, and VoxelJet actually was very keen on working with us and develop their technology to create this part. So this is the furniture that we made with the 3 legs integrated. It was done also during, I think, COVID time, so it was actually hard to progress in the prototyping, but we made it to work. You can see here the quality, and the underneath also is made in bronze, so we made the detail flush. And then we wanted to take it to a code-compliant, standardized, standard like the Euro code that we have in Singapore. And the idea was to use the system in a real place, like people can actually use. So we selected Gardens by the Bay to work with them. And they were very excited to be maybe the first to integrate a 3D printed stainless steel structure in a functional way. So we chose a small plot that they had vacant. It's just a green patch. It's actually not a very visited space in the gardens, but we found that was actually a quite nice spot where we had this point here. We have some reference points to the context, to different buildings that that are quite iconic there. This is a pavilion done by Thomas Schreffer. It's the SG50 dome, and there's other vantage points that are nice to capture. So our device, our floor plan was driven by the vectors of the views. So we created that pavilion there and the top of that green plane. And the idea was to create a bit of that kind of edge condition where you can look at somewhere. And we wanted to test some ideas here. We wanted to test maybe a cantilever, a ramp, an entrance. We wanted to explore some architectural features in this pavilion. So the geometry also created with tetrahedrons. You can see the unit of a tetrahedron here, the nodes, the bars. And then we work with the double skin principle, basically towards the edges, converges to Cygnus 0, and then opens up to get the depth to be able to withstand the loads. This is the idea for the geometry. And we work with Eurocode standards to meet the regulations in Singapore. It was actually quite challenging because they didn't use stainless steel before, 3D printed in any of the constructions. So it was very, very difficult to get it approved. So we had to run a lot of simulations, a number of detailed tests for them to be able to approve the construction to be open to public. So, well, we calculated it, we estimated the reactions, we basically adjusted the geometry. You can see here the size, the scale, something that people could enter, could lean, could sit down, could look at, could touch, something that could be accessible to everyone. And to generate the geometry, as mentioned, we work with this tetrahedral typology that allows us to optimize the structure, modifying the vertices. The nodes are generated with a more developed algorithm from the one that I showed at the beginning. The loads are determining the sizes of the bars. This is the way that the nodes are going to look like. And the generation entails a number of steps here. So, of course, we assign a certain diameter. We start working with, you can see here in number 4 is the convex hull structure, right? It's like basically a very low-res geometry, but it's consistent when we are applying it to the bars. Give us the nice tangent in a very simple manner. That's why, for us, convex hull has been kind of the way to go at the beginning of the geometry. Then we go with the section. We apply the thickness of a different thickness at the beginning. We go also for the connection system, the threaded connections, but in this case, the threaded is part of the node. We directly go for printing that we know is much better in comparison to standard nodes if we made it with traditional material, with traditional methods. But the most important thing here as well is that we are actually saving a lot of material compared to a solid node is 80% air inside. So it's actually very light. So we're printing a shell in the end. This is one of the nodes with all the systems integrated. And basically what we have is a system that allows us to almost real time adjust to the loads that we have and to the geometry that we have. So it is very fast. I mean, we're working with a script that basically takes only a few steps to create the geometry and a few more steps to design every single node and every single part involved in this components. So this is the first node that we printed. So it integrates standard bolts from M8 to M20, and the thread is also printed and calibrated, so we can directly integrate that standard components in. A total of 54 nodes were designed, where we were working with different details as well. So these selected here are the ones that are going to hold the frames, so they're flat on one end. So we implemented that in our script. You can select that some nodes are going to hold the panel, so they will cut that part of the branch and they will integrate a different detail. So we started looking at more specialized nodes. It's not only just purely structure, but also we have the foundations here. So the foundations also integrate a special, bolt to be connected to the foundation plate. And then this is basically the spectrum of the nodes. We have the weight, we have the dimensions, so we know everything about it. And then we print them and we code them in white, in this case, a selection that we had for the pavilion. We label them, and the labels in this particular project, we use a temporary label, so we print them. We use a color code to know the areas in which we're working, so it's easier to access the components. So we label them all, and then, this is basically the details that we are using here for our system. So this is the prototyping phase. Before we went to the final production, we used PA12 as the selection of material for testing. So we calibrated different bars with different diameters and different lengths to be able to optimize the diameter of the bars as much as we could. So we have 5 different types of bars. So according to the structure, we assign them. So most of them are of the thinnest diameter. Tensile tests were done, and majority of the cases, the bar was actually breaking and the node was actually intact. So that was very convincing, when it came to get the approval. Most of the samples actually broke on the bar and not on the node. We also run FEM for all the nodes, so they had information of all the nodes when we submitted the calculations, and we did our geometric prototypes to understand length, understand how easy was the system to be implemented on site. This is just a simple prototype to see how we're gonna connect them. We also used kind of a simple design for the caps. So the idea was to get them covered and continuous. So in the end, we can make it flash. And then we went to the assembly of the final prototype. We started printing the nodes, prototype in PA12. We tested the threads. The connection of them was actually quite smooth of the threads and the nodes. We started to put them together and to create this kind of 3-dimensional complex structure. This is the first version on the left, PA12. The right, you can see the nodes that we used by then. It's a stainless steel with it's a mix. It's not fully 100% the steel that we can print now, the 316L. So it was what we had then on our range. And but the performance was really, really good. The property that we couldn't meet was the elongation. Elongation was still not meeting the standards, but was enough for 3 years approval. And we made the assembly first in our campus. A team of, I think it's 6 people in total, using just simple tools and ladders. So the idea, the feeling was we're creating a very high-performing structure using our normal tools, feels like IKEA, but in stainless steel, right? So the system was very, very easy to put together. So that take basically 2 days of work, and then we 3D scan the structure to see if any deviation So we went to the site and started working on the assembly. Again, here we only got a construction company to help us with the foundation, because they wanted to have a foundation for it. We wanted just to have small ones, but they were, Gardens by the Bay was very strict with that. So we let them do the foundations. This is the final geometry of the different parts, the deck, the details that we had to support the deck. And this is the foundation that we had, and then this is the plates. The nodes are are connecting the plates, the standard plates in a very precise way. And this is how we are going to connect the nodes and the bars. 5 minutes. 2 minutes. So I will be fast here. Just the way that we connect the bars. I'm gonna run through a bit like the images that shows the complexity of the structure. And we wrap it with a upcycle fishing net. So that was the material that we chose for the cladding. 2 layers of that. The fishnet wrap took almost a week. So it was actually 10 times longer than putting together the structure. The structure was just a day. So that's, we did the load test. We started working on the deflection. The VCA people was there, witnessing that barely moved. So it was there, quite solid. And we were very happy about the outcome because, it was the first time that there was something like that built in Singapore. And for us was an achievement that we were able to go around the code and somehow be able to have it there open to people. So this is me, my wife, and my kid. This is how the structure looked at night. We put some LEDs so people could take some Instagram pictures. And this is how, we found people going there just to see the environment. So it was like something found, very light, very, we don't know what's that, right? It's like and then we got the PDA in Singapore. So then we started working with the government. And that led us to new exciting opportunities that I hope I can share in the coming years on residential structures. It's really good for extension when you cannot access with your trucks and your lorries. You can actually go deploy and extend your house. So we have this project ongoing. So hopefully we can show the final, the documents is submitted. So it's going to be approved. And 2 small experiences that will take me 1 minute. This is the COP28 Dubai that we did the pavilion for the Singapore pavilion, for the United Nations pavilion. So we basically displayed the technology, and it was really good because ministers and authorities were actually quite happy about the performance, the system, the easiness of it, and we're moving forward to take it to a larger scale. So that was the last year's pavilion, integrating waste and 3D printed nodes into one piece. And the last one that I just finished, and the pictures are from like the team that was there in Beijing. We created this cube structure using a very simple system of nodes and PLA and then recycled acrylic bars and PA12 nodes to create a relatively lightweight and complex network of cubes that is self-supporting. So with no additional structure, we used the diagonals. We put them to reinforce the structure what was needed. And became a quite iconic space for this festival. And you can see here the details and connections. So, well, that's the last slide. Thank you very much for, your presence here. You want to know more, we have this, 3D printing architecture book. But if you want to know way more, we can talk, and then we can discuss maybe over a drink or coffee after the talk. Thank you very much.
I was showing him this the sign saying 2 minutes because we have administration standing outside asking us to leave, which is also an interesting situation. So I'm not going to allow a question. I just continue and close the session. Sure. Thank you for presenting, and actually a lot of Instagram pictures. I absolutely copy that.
Thank you.
Thank you.
Thank you.
Applause for him.
Thank you.
Ollie always asked me to somehow close this with some kind of color. Ollie and me started this activity 10 years ago. This is number 10, which is interesting. And it's an event which we do each year. I do a lot of this kind of events, and I'm happy if they have them every second year or maybe every 3 years, because you need to have always this kind of brilliant speakers every year. Yeah, and each time when we finish this, it feels like, oh God, okay. okay, we made it. This is a super lineup, and it was a super lineup today. How are we going to manage next year? And each time it impresses. Each time it's really cool. We have two pieces of this. It's the exhibition, which we're going to see in a minute. Alex and team, thank you for organizing. That's the same situation. Each time you think, yeah, please. Each time you think, how are we going to make this again on this level? And this time it's really big. It's really big and solid pieces. Really impressive. That was very cool. Then there's the conference. Nadia and team, thank you for that. There's always this nice booklet, which I really appreciate that this is happening. And when we look at this, only 10 years, this is an evolution documentary. That's also something which really, really impresses. The conference, top lineup, quite diverse. Profession, gender, age. I'm the oldest, I'm sure. It's a platform for exchange, which also means it's a platform for competition. That's also something which pushes us and triggers us. And it's a family event. Moritz Mungenast, a colleague who's not having to speak today, came this morning first thing and said, this is where I always go to because I meet my colleagues and friends. That's something which makes me also quite proud that we're doing this. And Klaas was giving this comment. Next to all these nice tools, technologies, materials, you have to somehow get this in construction. Someone has to sign. That's also something which is, say, an interesting future challenge to come when I look at the, say, engineers in that field. In one of the very early BEAM events, we had one from 3XN here, and he said after the end of this, thanks for all these nice technologies and tools. What's the question? And I think we're actually at this tipping point. We're really getting to a lot of this kind of technologies developed. So there's a new technology which is to be developed. What do we do with it? How do we really bring this into construction? And this is the place where you're going to see this development. I really see this evolution of these processes. I close here. Thanks for being here. Thanks for the speakers to be here. Really appreciate it. Again, top line up. And I close it with announcing that we meet again in hall number 11-0 at F47, which is the BEAM stand, and there's beer. And that's it. This was a 2-minute thing. 2 minutes. This was a 2-minute thing. So we are in time. We have to leave now.
Everybody who registered for training points at the Chamber of Architects, Chamber of Engineers, may go to the reception desk and get their letter for the Chamber of Architects.